Hello and welcome to the Introduction to Python Microservices. In this section, we are going to explore the concept of microservices architecture. Understanding this architectural style is crucial if you want to build scalable, resilient, and maintainable applications, especially in a modern software development environment. So, what exactly is microservices architecture? At its core, it is a design approach where an application is composed of small, independent services. Each service, or microservice, is a self-contained unit that performs a specific business function. Unlike traditional monolith application, as you can see on the left-hand side of this diagram, where all components are tightly coupled into a single system. Right, so you can see here that we have one database. We have one business logic and data access layer. But if you come to the microservices application, you can see that each one of these microservices, which are performing a particular function in the app, has its own database that is connected to. So the microservice application means each service can be developed, deployed, and scaled independently of others. And now for the key characteristics of microservice. The first is independence. Each microservice runs as a standalone unit in the entire application. This independence allows teams to develop and deploy services without affecting the entire application. So you can work on each microservice independently. Now for scalability, microservices can be individually scaled. If a particular service experiences higher load, you can scale just that service, optimizing resource users. So you can actually scale based on the load that each of them are carrying, and I think that's really great. Then we go into technology diversity for microservices. For an app that uses microservices, since microservices are independent, the failure of one service doesn't affect the other. So it means that you can use different technologies, languages, and databases for different services, choosing the best tools for each specific task. We will be going into the practical dimensions subsequently. This is just to understand or have an overview of it. And now for the next point, we have resilience. Since microservices are independent, resilience boils down to the independence. The overall application is more resilient because the failure of one service does not bring down the entire system. It just brings out that service, and it can be fixed in isolation. So these are the basic characteristics of microservices. Now we go on to how microservices communicate with each other within an application. We have the HTTP REST. So this entails using RESTful APIs, and you also have gRPC, and you also have RabbitMQ, which we're going to treat in the course of this project. Now we go into the advantages of microservice architecture. First, we have faster development and deployment. So independent teams can work on different services simultaneously, meaning each of these services can be worked on simultaneously, leading to faster development cycles and more frequent updates. Now we have improved fault isolation. If one microservice fails, it doesn't necessarily bring down the entire system, making fault isolation easier and more effective. For easier scaling, services can be scaled independently based on their specific needs, rather than scaling the entire application, which has actually been said before. Now we have technology flexibility. Teams have the freedom to choose the best technology based on the characteristics that the microservice can make use of. And this can drive innovation and efficiency. Now we have the challenges. We want to go into the challenges of microservice architecture. Now, the first challenge is the increased complexity when managing and orchestrating multiple services, each with its own dependencies. So each microservice having their own dependencies adds complexity to the system. Because we are working with different microservices, different technology, different dependencies, it increases the complexity. Now, data consistency. Ensuring data consistency across distributed services can be difficult, especially when dealing with transactions that span multiple services. Data consistency across distributed services can be difficult because they are actually isolated in themselves and their independence and working with their own database. And so, data consistency can be a difficult thing. Inconsistency can be a thing in microservices. In microservices architecture, the next is monitoring and debugging. With many independent services, monitoring and debugging issues can become more complex and require sophisticated tools. Now we go into network latency. Communication between services over a network can introduce latency, potentially impacting performance. Now we're going to go into when to use microservices. Now, I'd like us to note that microservices are not one-size-fits-all solution. They are most beneficial in large, complex applications that need to scale rapidly, have distinct modules, or require high resilience. However, for smaller projects, a monolithic approach might be simpler and more cost-effective. It is essential to evaluate your project's specific needs before deciding on a microservice architecture. If your project requires frequent updates, independent scaling, or involves a large team working on different parts of the application, microservices might be the right choice. So this is an overview of microservice architecture. By breaking down your application into smaller, independent services, you can gain flexibility. Like earlier mentioned, you can gain scalability and resilience. However, it's important to consider both the advantages and challenges, as earlier I treated. In the next session, we'll dive into how Python can be used to build microservices, including setting up your environment, your integrated development environment, and creating your first service. Stay tuned. Welcome to this tutorial video on why you should choose Python for microservices. So, in this tutorial video, we'll be answering the question of why Python is suitable. Why is it a suitable architecture for microservices? Now, microservices is an architecture style that has become increasingly popular due to its flexibility, allowing developers to deploy updates and scale services independently. Now, Python is perfectly suited for this architecture because of its versatility and developer-friendly features. The simplicity of Python syntax, combined with its robust ecosystem, makes it an ideal choice for microservices. It enables developers to focus on the business logic while benefiting from a rich set of tools, libraries, and frameworks. Now, simplicity and readability are core strengths of Python, especially in the context of microservices where developers need to manage many independent services. Python's minimalistic and readable syntax allow for faster development and reduces errors. This means that even in large-scale microservices, architecture developers can focus on functionality rather than getting broken down by complex language. Syntax debugging is also simplified thanks to Python's clear error messages and low-code complexity. Now, one of the key reasons developers choose Python for microservices is its large range of libraries. Frameworks like Flask, Django, FastAPI enables fast web development, while libraries like Request simplify HTTP communication. For more advanced tasks, data analysis tools such as Pandas and NumPy come in handy. Python's rich library ecosystem allows developers to rapidly prototype and develop services without even building every function from scratch, which makes it an excellent choice for complex microservices architecture. Now, containers in particular, Docker, is an essential tool for deploying microservices because they allow the services to run in isolated environments. That's the key. We are creating smaller services that make up a whole system. and Docker enables us to run those services in isolated environments. And Python's compatibility with Docker makes it an ideal language for building microservices that need to scale quickly and efficiently. So, due to Python's lightweight nature and the absence of a heavy runtime environment, containerized Python services can be deployed and scaled with minimal overhead. This means that without needing a heavy or complicated software, Python programs can be packaged in small, self-contained units, which are called containers. And these containers make it easy to set up and run programs on any computer. And if more space is needed as the program grows, it can be increased without much effort or cost. Additionally, Python's vast ecosystem of libraries ensures a smooth integration with container technologies. Now, to summarize, Python provides a perfect balance between simplicity, flexibility, and efficiency, making it a highly effective choice for microservices development. Its extensive library support, coupled with compatibility with modern containerization tools like Docker, enables faster development, better scalability, and easy maintenance. So when you're working on web services, data processing, tags, or even machine learning microservices, Python's development-friendly environment ensures a smooth workflow. And its versatility across different programming paradigms and ecosystem of tools make it the language of choice for scalable microservices architecture. So thank you. This is a short overview of why we choose Python for microservices. Thank you. Welcome to this tutorial guide on the step-by-step method to install Python and pip on Windows. So we are going to be using Python for creating microservices, and in this tutorial we will help you set up everything quickly. And I'll also walk you through how to download Python, install it, and ensure that pip, which is Python's package manager, is also installed correctly. Let's get started. First step is to open your browser, and then we are going to go to the website python.org. This is the website for downloading Python. And on the homepage, you can notice that under the download section, the site automatically suggests the best Python version for Windows users. So just go ahead and click the large download button and make sure to save it to a location you can easily access later. Alright, so now that Python is successfully installed, we can now navigate to our download folder. Then we are going to double click on the installer, and you should see a setup window, just as you see here. One important step is to click the add python.exe to path, and this ensures that you can run Python and pip from any location on your computer using the command prompt without having to navigate to the specific folder where it's installed. Then you need to click install now and wait for the installation to be completed. Now your Python has been successfully installed, we need to verify that it has actually worked. So we need to click on the Windows button +R and then type cmd and then enter to open our command prompt window. Now to verify Python installation, just type Python enter and we should see a Python version 3.12.6. So by default, pip, which is Python package manager, is also installed along with Python. So to check if pip is working correctly, we are also going to type the pip version of this and enter. And you should see the version number of pip, which means it has been installed successfully. Now, the next thing you want to do is to see if pip is working properly by trying to install a Python package. So in the same command prompt, we need to type pip space install space request. And request is just a package used to make HTTP requests in Python. So our request package has now been installed. Now we will type pip space show requests, show request, and you should see some details about the request package, confirming that pip is running or is functioning as you'd expect. And we need to be seeing the version number 2.32.3. And congratulations, you've successfully installed Python and pip on your Windows machine. Now we are ready to start coding in Python and using pip to install packages. Thank you, and see you in the next video. In our last tutorial, we installed Python and pip on our Windows platform. And in this tutorial, we are going to be creating a virtual environment on Windows. And for this, we are going to be using Visual Studio Code, which is an IDE, an integrated development environment, which is basically an application that helps programmers develop software code efficiently. So we are first going to download Visual Studio Code. We'll need to go to the website code.virtual.studio.com. It will take us to the Visual Studio Code website, and then when you're there, you need to click the Download for Windows button, and the download should start immediately. Alright, so your Studio Code installer is downloaded. We now need to navigate to the downloaded folder, and then we can double-click to run the setup. And we can also accept the agreement. Next, this is your directory for the installation. Now, it already exists, so just click Create a Desktop icon and then Install. Alright, so our Visual Studio Code has been installed. Now we can launch it. So now we can start creating our virtual environment. First of all, what is a virtual environment? Well, it's a special tool in Python that helps you to manage different dependencies for your projects in isolated environments without using virtual environments. Every package you install affects all of the projects on your computer. This can lead to conflicts when one project needs a specific version while another requires a different one. So let's say you have two projects, Project X and Project Y. Project X needs version 2.0. And Project Y needs version 1.0. If you install both projects globally on your system, it can create conflicts. So virtual environment enables you to be able to install the different versions in different environments. So now the first thing to do is to create your project folder. Just go to our C drive and create a folder called Project. So we have created a folder project and then we need to select it. So Python comes with a built-in model called venv to create a visual environment, but this is if you are using Python 3.3 and above. But you can still install the virtual environment using virtualenv if you are using older versions of Python. The first thing we do is we need to go to View and select Terminal. Here we are going to change this to command prompt, and you are going to type pip space install virtual. If you are using Python 3.0 later, this is not necessary, but I'm just doing it for older versions, right? So now let's create a virtual environment. Once you are in your project directory or folder, you can type python-m-venv-myenv. MyEnv here is the name of the virtual environment. You can name it anything, whatever you want to name it, and then hit enter. So now we have created our virtual environment, and we need to activate it. So we are going to type in command prompt env script activate.bat. And we should see that our virtual environment has been activated, and we can just go ahead to verify and install a package using pip install request. So your request package is installed, and you can verify this by just typing pip space list, and it should show you a list of dependencies. And now you can create a requirement.txt file to list all the dependencies in your project. This file can be very helpful because you can share it with other developers to help them recreate your environment. And you can do this by just typing free space requirements.txt, which creates a requirement text file which contains all the dependencies in your environment. And finally, we can deactivate environment by typing deactivate. So you should now be out of your virtual environment. And thank you very much. In this tutorial, we covered how to create a virtual environment. Thank you. Hello everyone! Welcome to this tutorial video on the overview of Python Microservices framework. In this tutorial, we are going to be looking at what a microservice framework is. We are going to be looking at types of microservices, Flask, and FastAPI. And we are also looking at choosing the right framework for your microservice. The first thing we are going to be doing is defining microservice. So, what is a microservice framework? Well, a microservice development framework is like a collection of libraries, models, and functions that simplify web app development by extracting low-level details such as protocol handling and thread management. So you can think of a framework as a toolbox that makes websites easier. Instead of doing everything from scratch, like writing code to manage how a website talks to a server or how pages load, the framework handles those details for you, so that you can focus on creating the website features like forms, buttons, employees, without worrying about the behind-the-scenes work. So what is Python's role in web development? Well, Python acts as a powerful universal language that offers a wide range of frameworks to suit different application needs. Some examples are Django, Flask, and FastAPI. Django is often used for full-scale web development applications, while lightweight microservices are done with Flask and FastAPI. And these have become popular choices for microservices development because of their simplicity and performance advantage. So we are going to explore these frameworks in modern microservice development. The first one we are looking at is Flask. Now, what is Flask? Flask is one of Python's most popular frameworks for developing web applications, particularly when it comes to microservices. Its minimalistic design keeps the core simple, allowing for easy expansion through extensions and third-party tools. Flask enables rapid prototyping and is highly suited for building APIs, which is why it is trusted by companies like Netflix and Reddit. So its lightweight design makes it an excellent option for creating microservices that can scale without the overhead of more complex frameworks like Django. Now we are moving on to FastAPI. FastAPI is quickly becoming a go-to choice for development for modern high-performance microservices. It has native support for asynchronous programming, making it extremely fast, often compared to Node.js and Go in terms of speed. This basically means that FastAPI is designed to handle many requests at once, making it a great high-performance app, unlike those that need real-time updates or save a lot of users. This means it allows developers to write less code while still getting powerful features. And with FastAPI's built-in data validation and automatic API documentation, FastAPI significantly reduces development time while improving code quality. It is especially useful in scenarios that require processing large numbers concurrent requests, such as real-time data applications or distributed systems. So what? This means that FastAPI is designed to handle many requests at the same time, and makes it ideal for applications that need to process real-time data, or manage large-scale systems like chat apps, live dashboard, and online platforms that saves a lot of users at once. Now we are going to be comparing the differences between Flask and FastAPI. When comparing these two for microservice development, several key differences emerge. FastAPI offers asynchronous capabilities out of the box. We have talked about this. It is able to run many tasks at the same time, resulting in a superior performance, especially for new concurrent requests. Now, Flask, on the other hand, is the most suited for synchronous tasks, but it can still be extended to support asynchronous tasks through additional libraries. Another difference is that FastAPI also excels in data validation, where it automates most of its processes, whereas Flask requires manual validation, making development slightly more complex. Lastly, Flask benefits from its extensive community support due to its longer existence, while FastAPI is rapidly growing in popularity, offering built-in documentation tools like Swagger. Basically, what we are saying is that because Flask has been in existence longer, it has a bigger community support. And we are seeing that Flask is better for synchronous tasks, although it can be extended to support asynchronous tasks by adding libraries. And that FastAPI is better for asynchronous tasks, where asynchronous here means that attacks are happening independently without waiting for each other. Now we are going to move on real-world examples of Flask and FastAPI. In microservice, so in real-world application, Both Flask and FastAPI have demonstrated their value in microservice development. Flask is used by companies like Netflix and Reddit, where its minimalistic design helps manage microservices and API efficiently. Now, FastAPI, on the other hand, has seen growing adoption by companies like Uber and Microsoft due to its speed and ability to handle asynchronous requests well. This has made FastAPI the go-to best choice for applications requiring high performance, such as real-time data processing and cloud-native applications. Now, both frameworks excel in different areas, offering developers flexibility in choosing the right tool based on the needs of their microservice architecture. Now we want to go into detail on choosing the right microservice architecture or development. Now, both FastAPI and Flask offer unique advantages in Microsoft development microservice development, meaning they both have the advantages. Flask is ideal for smaller services, where simplicity is key, while FastAPI is performance and scalability. So we are saying that Flask is made for simplicity and FastAPI is made for performance and scalability, making it a better transfer application dealing with high traffic and asynchronous workload. The decision should be driven by specific needs of the project, whether I prioritize the ease of development or the high performance. With both frameworks widely adopted, the industry's Python developers offer a wealth of options to build scalable and microservice framework. So in this tutorial, we have looked at what a microservice framework is. We have looked at Flask and FastAPI, at real-world use cases for both frameworks, and at choosing the right framework, as well as the differences in comparison between Flask and FastAPI. Thank you. Hello everyone. Welcome to this tutorial where we are building our first simple service using microservices in FastAPI. Now, we've already gone through Python framework for microservices Flask and FastAPI. So, in this tutorial, we'll be building a web service or a microservice using FastAPI. To begin, we are diving straight into the code. The first thing that we have to make sure of is that we're in our virtual environment. We've already gone through how to do this. So the first thing that we're going to do is we're going to install FastAPI using pip install FastAPI. We should see that FastAPI. Alright, so the FastAPI is installed. Now we'll go right into creating the file. I'm going to name it main.py. Alright, so now we are going to import the FastAPI class in the FastAPI library. And next, we are going to create an instance of this class using app equals FastAPI closed brackets. So what it means that this app is going to hold our FastAPI app. So now we go ahead to defining the routes. All right, so we are going to define the path operation in the function. So path here basically refers to the last part of the URL starting from the first slash. So this is the root path. This is the root path. ROOT. /items. The /items here will be the path. So a path is commonly called an endpoint or a route, but they have differences, and we'll look at that in subsequent tutorials. And the operation basically refers to one of the HTTP methods, which can be either post. You can have @app.post, @app.get, @app.put, or @app.delete. And this basically tells the FastAPI function that the function right below is in charge of handling requests that go to this path defined up here. And this syntax here is basically called your decorator. Something that starts with the @ symbol is basically called your decorator, and the decorator takes the function below and does something with it. So in this case, the decorator is telling FastAPI that the function below corresponds to the path / with an operation get. And this is the path operation decorator. And the function is defined with async because the application doesn't have to communicate with anything else or wait for it to respond. So you can use the async, and if you don't know whether there's any communication, then you can just delete this and you have defined a normal function. Alright, so now that I have defined our app, it's time to run it. To start the FastAPI development server, all we need to do is to run a command, fastapi -dev, then main.py. So when you run this command, FastAPI starts a server. I think there's a mistake here. So we have to install FastAPI. We type pip install FastAPI, bracket standard, close bracket. Then we run the command again. So when you run this command, what FastAPI does is that it starts a server and gives you a URL where your app is being hosted locally. So you see the URL here. You can follow the link, control, then click on the link. This line tells us that our app is running on this local host and FastAPI uses Unicorn, which is a lightning fast server to serve the app. However, there's another way to run the app, and you just have to include it in your Python file. So, if you add this block of code to your Python file, it allows you to run the app directly. Now, this here is a normal Python declaration, meaning that whenever the file is run, the code runs directly. And we are going to Unicorn, which is basically a server on which your app will be run. So we are essentially telling the Unicorn to run it on this particular port. So we can just even change this. Okay, we can maintain this. So now we would open another command prompt, and remember to save this one. And now we are going to run into python main.py, and we see how it runs. All right, so we are seeing our link here. So we follow the link here, control, and then click the link. All right, so if we are to open our browser here, we see that our app is also running in this host, and this was for the previous one. And that brings us to the end of our tutorial. So in this tutorial, we have created a simple FastAPI app, and we defined the get endpoint that responds with the JSON message, hello world. And we ran the server and tested it in the browser. Thank you. Welcome. In the previous tutorial, we created a simple microservice using FastAPI. And in this tutorial, we are going to be defining routes and endpoints in FastAPI. So what are routes and endpoints? Routes are the parts in your URL that define where the client will interact with your web service. And endpoints are the combination of routes and then the HTTP method, either get, post, delete, used to handle specific requests. All right, so let's run by a quick example to familiarize ourselves with defining routes and endpoints. So we are going to create a new file. We name it app.py. So we just copied the first line of code here. Remember that we are importing our FastAPI class, and then we are creating an instance of this class. Now, I want to define a path operation, decorator, and function. So in this video, we are going to define a different route. So in this block of code here, what is happening? We are creating a route, and the route here is users/user ID. And the user ID is in curly braces. Cut is in curly braces. This is a path This is a path parameter, meaning that it's dynamic and it can be any integer. So that's why we have int here. And so what happens here is that the FastAPI function, get_user closed brackets, handles the logic when this route is assessed. When this route is accessed. So in this case, it just returns a simple JSON response with ID and username. So we are seeing that whenever this route is accessed by the client, the function getUser simply returns a JSON message with user ID and the and the ID imputed and the ID inputted by the client. The name here is a string, and then we have the ID inputted by the client. So we understand what the route is. The route in this cell is user/user_ID. Now, what is the endpoint? So in this example, the full endpoint is get plus the route. So that's the method, the HTTP method plus the route. So you can use different HTTP methods with the same routes to define or to create different endpoints. So you can get post here. so you can get app.post for the same route. So a path is, or a route is actually the structure of the URL. So it basically defines the structure of your URLs. The endpoint is a combination of the route in the HTTP The endpoint is a combination of the route in the HTTP methods to handle specific requests. So with FastAPI, you can easily define routes and endpoints. Okay, so right now we are going to run our program. Make sure to always save. So our application is up and running, and we can just go here to see. Sorry, we made a mistake. We ran the previous code, so it's supposed to be app.py. Alright, so we just click this. What we are supposed to do is that we copy this. This is our URL, and we are going to add this route here. That is, I'll add the integer and see how it runs. And you can see the output showing the user ID. Then we come back here, we see the message successful. This brings us and this brings us to the end of this tutorial video on defining routes and endpoints. Thank you. Hello everyone. So in this video, we are going to learn about the most common HTTP methods: get, post, put, and delete. We have already looked at defining routes and endpoints. We have looked at framework for microservices, FastAPI, and creating a simple microservice. So now we are going to the HTTP methods. What are the HTTP methods? Well, these are like instructions that tell the server what to do when you interact with a website or API. So, like we did in the previous tutorial, in defining routes and endpoints, we use the get method, and the get method simply retrieves data. Whenever this route is accessed, the get method receives or retrieves data and then returns the data here, which is the user ID that is dynamic and provided by the user. It then returns the user ID and then the name. And then the name, as we saw in our previous. And then we also have post, which is used to send new data to a server. And then we have put, which is to update existing data. Finally, we have delete, used to remove data. So now we are going to create a post endpoint. We've already been through get, so now we are going to use post. For the post method, as I said, it is used to send you data to the server. For example, if you are signing up for probably a new account, or if you are submitting a form, then you are using the post method. Now let's create a new file called post.py. Helicopter. So now let's create a new file called post.py. We are going to import FastAPI, and then we're also going to import the base model. Pedantic is a kind of data validation library used in Python. It allows you to define data models in a structured way. It essentially ensures that the data you are passing is valid. And then the base model is a class in the Pedantic library so that it inherits from base model. And it defines a data model that has a specific field or, if you like, attribute along with their data types. So it has specific field and the data types. So what happens that Pedantic uses this model to validate a serialized data automatically to ensure that basically the FastAPI handles validated data for route automatically, ensuring that your data is already verified before using it. Alright, so here we are creating a route /items. So we have to create an instance. So app equals FastAPI closed brackets. So we have to define a class item. So basically we are using the base model class to define the structure of this class item. We are seeing that this class item is inheriting from base model, and this is the structure of it. So here we are creating route items where users can submit data. So we've defined a new class item to describe the data structure, like the name and the price of an item. So whenever the post request, which is the HTTP method, is made, it returns a message saying that the item was created. Now, one of the great features of FastAPI is the interactive documentation it automatically creates. So we're going to run this. Sorry, it should be post.py. So we are just going to copy this link right here and we paste and add /docs. So we can test the post method right here and fill in the item and price, and then we'll execute and you see the name in real time. All right, so we just go here and then we can change a string to max and then we execute. So we see here in the response body, there is item max created with price 10, right? So now we move on to the puts method. We are going to copy this code and create another file called out cut. So we are going to copy this code and create another file called put.py. We are going to adjust this code to put here items, and then we are going to create a dynamic /item.id. We have to close our running application. So now we have output here. So in this in this example, we are using the put method to update an item by its ID. So when you pass an ID in the new item data, the FastAPI returns a message saying that the item has been updated. So the item with item ID has been updated to the name with the price. All right, so we can run this too. Now we just go to our browser and update this. So we can see that it has changed to put. Here you can just try it out. Then input 10 as your item ID and change this to say Matthew and price to 11. You see that it responds that item 10 has been updated to Matthew and price 11. So this is updating a particular item by its ID. The item here is the class with the name and the price. Now we are going to use the delete method by using the delete method to remove an item by its ID. So when you send a delete request, it returns the message confirming the deletion. So I just need to save this. UVcorn automatically detects the changes. So go to our browser, we reload, we say delete. You can also try this out. And we can see that item 10 has been deleted. And that brings us to the end of our tutorial. So we said that the get lets you retrieve data, the post is for creating new data, put is for updating existing data, and delete is for removing data. And these methods make up the basic actions you perform with APIs. In our next video, we'll be looking at JSON handling and response formatting in detail. Thank you. Welcome to this tutorial video on JSON handling and response formatting. So we've already looked at handling HTTP methods, and we've also looked at defining routes and endpoints. So in this video, we are going to look at the different ways to format a JSON response, and then we are going to look at how to handle the responses. So basically, we are going to start with this. This is a simple microservice that contains a dictionary and message. Hello world. And we are saying that naturally, FastAPI transforms the dictionary into a JSON response. So looking at this route and endpoints, we see that anytime this route is accessed, we see that anytime this route is assessed, we are simply going to run this Python function, route closed brackets, which is going to return this message. So we are now going to run this program. So we're going to use UVcorn and then the file name, which is main, and then the name of the API instance on line 3, and then reload. So you can access the application on this URL. This is a typical JSON response. And now we want to also look at another example here, which is this microservice which uses also the get method. And the route is defined here, and the user ID is dynamic, meaning that it can be any integer, and it's going to return a dictionary with user ID. The user ID is the integer that is going to be added to the root. And then we have the name here, so we can also run this. So just simply exit this, and then we run unicorn, and then this is the name of the app, and the name of the instance, and then reload. All right, so we already have the link in our browser, so we're just going to add this part to it, /users/1. You can make it 3 or any number, 6. So for user ID, cut. So for user_ID 6, the name is John Doe. So this is a JSON response. We are saying that FastAPI always transforms the dictionary into a JSON response, and this is the format of the JSON response. So now we're going to look at another important thing, which is extracting JSON with pedantic models. Now we've already had an example using the post method where we used pedantic model. So we said that basically FastAPI uses pedantic model to define the structure of response. And this ensures the type value is correct, meaning the response or whatever is being imputed to the server, or whatever is being inputted to the server has the same type as the pedantic model. So we are saying here that in this microservice with FastAPI, item here is the pedantic model that specifies the data structure. So the data structure has name, which is a string, and price, which is a fruit. And then you have your HTTP method and you have your root. And we are seeing that this is added here so that the data matches the expected structure. So we are saying that this response model is going to validate the data with the expected structure. Here, the function that is called anytime. Here we have the function that is called anytime this particular endpoint is accessed. So we have the item name and the item price. So FastAPI is going to convert this into a JSON response with this structure, with the structure of the pedantic model item. So, of course, we want to test this out. We can just exit this and then we can run this app, which is going to be post. The name of the app is post.py. So we need to run this, and now we are going to test this because a post method here, it basically means that we are sending something to the server. The client sends something to the server, so you just use the FastAPI documentation, which is /docs. We are going to test it here so we can try it out. And now we're going to input any name, for example, Margaret, and the price is 30, and then we execute. So if we are able to test this in command line, this is what we'll be using. And then we see that this is the JSON response, and this is a response code 200, and this is the message associated with it. All right, so now I want to look at handling custom JSON responses with status codes. So you can customize responses, including certain different status codes, like 201, which means created, or 400, which is a bad request. And this is useful for creating or handling errors. So we're going to use this for our response.py, which is a simple response with post as the HTTP method. And the root is defined here. And then we see the function here, create item. And we are saying that whenever we post data, it will return a 201 status code. And we are saying that whenever we post data, it will return a 201 And we are saying that whenever we post data, it will return a 201-status code created. And then that response alongside a JSON message. So we have this JSON response having 2 arguments. One for the status code, which is 201 created, and then one for the JSON response message. So we can also run this. All right, now we want to check this. So once again, go to our FastAPI documentation, and here we reload. So it's basically the same. We reload this, and then we try that. So again, we can use any name, for example, John, then execute. This is for you if you want to try it in a command line. You add this to the root. So we are adding this, we are posting this data to the server. And we have 201 here, which is the response code. And then we have the message here, name created, item created, and the name is John. Now we want to look at a more complex method. Now we want to look at a more complex example. In the case of when you have more complex data, like an item and its supplier, we are looking at nested JSON structures. We first need to create a new file, nest.py, so we use this code. In this code, we have two pedantic models, supplier and item. The supplier has a structure of name and location. An item has a structure of name, price, and supply. And we are saying that we are going to use the getHTTP method, and we are using this particular route. So item here has a nested supplier model. It basically means that the supplier model here, which contains your name, and then your location, is nested in the item, which has the item name, the price, and then the supplier. So this is an example of having nested JSON responses. We are saying that whenever this endpoint is accessed, this function with item is called with a particular integer here. And then the response is going to be your name, your price, and the supplier, which is also a pedantic model, which is nested in the item pedantic model. So we just save this. I think we can save this. I think when we save this, we can just run it directly. So we can check here and you can reload. All right, so we just escape from this and then we reload for nests.py. All right, so now we go to our browser again and then refresh. Yes, so this time we have the right thing here. Just try it out. Input an item, ID 1 or 12 out of execute. This is the curl method of doing it on the command line. And then, so we have our response body. So we have this JSON message, the name, price, and the supplier containing another JSON response. So we have here a nested JSON response. All right, thank you very much. In this tutorial, we talked about handling JSON responses and response formatting. So we looked at using pedantic models to structure our JSON response. We also looked at handling nested JSON responses. Thank you very much. Hello everyone, welcome to this tutorial of building a simple Flask app. Alright, so in our previous videos, we looked at building a simple microservice with FastAPI. And now we want to know how to do this with Flask. So in this video, we'll be looking at how to create a basic Flask application. The first thing that we do is that we create a new file. The name is my_flask_app. Alright, that should be .py. So now we have installed Flask. If you don't have it installed already, just install it. Then we can go cut. Now we can begin to code and also create our app. The first thing we need to do here is that we import our Flask class from the Flask model. The next thing is that we are going to create, just like we did in FastAPI, an instance of the app. But this time we are going to create an instance of Flask and we are going to name it app. Alright, so now we have created an instance of our Flask application and we have named it app. Now we are going to configure our root and our endpoint. Here, our decorator, which is on line 5, defines the root of our web app. Defines the root of our web app and the home function. And the home function retains a simple welcome message stating welcome to Flask microservice. So the next part of our code is that we are going to run the Flask development server, and we are going to do this in debug mode. Alright, so we know line 9 is a normal Python function call, and then this is simply running our development server in debug mode with the app. Alright, so the next thing is that we're going to save. So the next thing is that we're going to save, we are going to run the app in our terminal, we are going to use Python and then the app name. We are going to use Python and the app name is my_flask_app.py and then we run it. So the problem here is that the Flask app was created in a wrong folder. So I'm just going to move it to our project directory save and then we can just run it again. So to this cut. This means our app is running on this server. So we just click it. Then we see the message, the welcome message, welcome to Flask microservice. So we can see that in this example, the root here is defined and we see the decorator on line 5, but we don't see any HTTP method. This is because Flask uses get as the default HTTP method. So now we are going to define another root. Okay, so we're going to also import from Flask, all right? And then we just save this, and now we can copy this. And then we'll add the root, or we just add the root /hello, and we see JS on cut, and we see JSON response here. And we see this is the home root, and this is the hello root. So what we have done is that we have created two roots, and this returns a simple dictionary, and this returns a JSON response, because your JSONify here takes a dictionary and turns it into a JSON response. All right, and that brings us to the end of the tutorial. Cut, and that brings us to the end of the tutorial. So here we have learned how to use Flask to create a simple microservice, and we have also learned how to define different roots. Alright, welcome to this tutorial video. Previously, we've looked at creating a simple microservice with Flask, and now we're going to look at handling HTTP methods and request data in Flask. So remember that in our Flask app here, and define two roots. So remember that in our Flask app here, and we define two roots. So now we are going to add HTTP methods. So HTTP methods, like we previously discussed for the FastAPI, involve methods like get, which retrieves data from the server. For example, like fetching a list of items. And post sends data to a server to create a new resource. For example, adding a new item and then put which updates existing resource with new data. For example, modifying an item. And then we have delete, which removes a resource from the server. Alright, so first we are going to go into handling get and post requests. So we are going to create a new file and we are going to name it methods.py. So you can just go ahead and copy this. Every time we are starting an application, we have to import Flask and then create an instance of the Flask app. The next thing we do is that we are going to configure our routes and add the method to create our endpoint. Alright, so here we have on line 5 our path decorator, and we see the path or the route which is /greet, and then the method which is the get HTTP method. And then we see that anytime a get request is made to /greet, it's going to return a JSON message. Hello and welcome. So we already explained that the JSONify here transforms a dictionary into a JSON response. So this is an example of using the get method. And remember, in our previous video, we did not declare the method, and we said that by default, the method is the get method. So now we are going to build an endpoint to accept JSON data. Remember, endpoint is your route plus your HTTP method. And so this time, we are going to be using the post to build an endpoint to accept JSON data. Remember, post requests are used to send data to the server, so we are going to use this block of code. We can see that on line 11, we see the route and we see the method which makes up the endpoint. And for this, we have to import request library in our header. Alright, so request.json on line 13 allows us to extract the JSON data sent with the post request. So when the post request is made, the request.json allows us to extract the data sent, and we are fetching the name field from the JSON, and if the name field exists, we are going to return a personalized message, which is the JSON message with hello, and the name and the value in that name field. Now, however, if the name field is not provided, we return an error message with status code 400, which means about request. So now we also have to run our development server. So we just input a block of code to run the development server in the debug mode. And we are saying that it should be run directly. And then we have to make sure that our file is in our project directory. And then we are going to run python methods.py. So now our development server is up and running. We are going to open new command prompt, still in our virtual environment. And then we are going to use this code here to test if our app is working correctly. The curl here is just a command tool for sending request to URL. And we are saying that this here is specifying the method as post. We are sending the data to the server at this particular URL. And then the header tells the server that the request body contains data in your JSON format. And this here indicates that we are sending data in the body of the request. And in this case, we are sending the name as the key and then John as the value. So we hit enter and we see that our message has been sent correctly. Now, if we were to change the name to age and enter, we see that there's an error message. And if we check our server, you see the code 200 and the other sends 400. So now we are going to do the delete method and the put method. Alright, so the first thing I will do is I need to create a new file. We are going to limit methods2.py. So we are going to import our modules and then create an instance of the app. And now I go to configure or create an endpoint, a root and an endpoint using the put and the delete method. So we first start with the put method, and we remember that the put method or put requests are used to update existing data. So here we have created a root that simulates, So here we have created a root that simulates updating a resource. And here the resource ID is passed as a URL parameter, as we can see on line 5. And then when a put request is made, we return a message indicating that there is a resource with that particular ID was updated. And we now go to the delete method. So this is also configuring or creating a root and an endpoint to the delete method. So delete request, remove resources. And in this delete route, we are simulating the deletion of resource with the provided ID, and it returns a success message. Alright, so we also have to run the development server, the Flask development server with this block of code here. So we are running it in debug mode. So now we have to exit this. So hit Ctrl+C, and then we can save this, and now we are going to run Python methods2.py. Alright, so our development server is up and running. So we go to our command prompt. Now we want to test this, so we are going to use this code. We've already been through using curl, which is used to make requests to servers. So we are going to make a put request to this particular URL, with one being the ID parameter. So we just enter this and we see that resource 1 has been updated, meaning that our code is working properly for the put. Now we'll do the same for delete. So for the delete, we will use this code, which simply sends a delete request to this URL. And the resource ID is 1 as well. You can change the resource ID, so we can even try 3 and enter. You see that resource 3 is deleted. And this brings us to the end of the tutorial about the HTTP method, get put, delete, and then post methods. Thank you for listening. Welcome to this tutorial video on understanding containers in Docker. So in this tutorial, we are going to look at what are containers. Why are containers useful? Containers versus virtual machines, Docker overview, and advantages of using Docker. The first thing we are going to look at is what are containers? Well, you can think of containers as tiny, self-contained packages that hold everything an application needs to run. Like it's called libraries and settings. In a typical illustration, imagine that you have a recipe that works only perfectly in your kitchen. And when you try to make it in someone else's kitchen, you run into problems. Because, well, you might have different ingredients, tools. And Docker or containers solve that problem by packaging everything together so that no matter where you cook, whether it's on your computer, in a cloud server, the recipe turns out exactly the same every time. This means that developers can move the applications easily from one place to another, whether they are testing it or putting it online. It also means they don't have to worry about things breaking or needing to adjust it for different environments. And containers make it easier, faster, more reliable, and less complicated to get applications up and running. Now, containers and virtual machines, or VMs, containers and virtual machines are both types of virtualization, but their key distinction lies in their approach to virtualization. VMs act like completely separate computers, each with its own operating system, even though they are all on the same physical machine. This gives them strong isolation, but makes them heavier, slower, and require more space, because each VM has to carry its own full operating system. But containers, on the other hand, are much smaller and faster. So instead of each having its own computer, its own operating system, containers share the operating system of memory machine, which means they use less space and start up quicker. They only carry what is needed for the application, making them more efficient than VMs. We are now going to look at Docker, an overview of what Docker is. You can think of Docker as a set of tools that help create and run containers. This means that it's a containerization platform which helps build, deploy, and manage applications as containers. Now, there are the main parts that work in Docker, with the first being the Docker image. You can think of this as the blueprint or the recipe for the containers. They contain everything that's needed to run an application, such as code and settings. Once they are created, they can never be changed, meaning they are immutable. So, Docker images are the blueprints for containers, and they contain all the necessary dependencies. Now, Docker daemon. What is Docker daemon? Docker daemon is a background service that does all the heavy lifting. So it builds, runs, and manages containers and images. It's like a worker that listens to commands and makes sure everything runs smoothly. Another thing also is the Docker client, which is what you interact with. It's a tool you use to send commands to Docker daemon. It's what you used to send commands to Docker daemon, like telling it to create a container to start an application or stop one. So all these parts work together to make sure applications run in a neat and organized container, or containers. The next thing we are looking at is building and running Docker containers. So the Docker file contains the instructions to build the image and defines the base image working directory, the files to copy, and the command to run. And we'll be building a Docker file for a simple microservice in the next or in subsequent videos. So a Docker file can be thought of as a set of step-by-step instructions for building a container. And it tells Docker what to do, like what base to start from. That's what templates you are using, or what's the starting point, and what files and programs to include. So once the Docker file is ready, Docker follows the instructions to create the image. And the image is a snapshot of everything needed to run an application, all bundled together. And the Docker run command is used to start the image, creating something called a container. So the container is where the application runs, but it is in its own bubble, so it doesn't interfere with other programs on your computer. By doing this, Docker makes sure the application behaves the same way, no matter where it's running, whether it's on your computer or somewhere else. Now we want to look at the advantages of using Docker. First is portability. Once you pack your app into a container, you can run it anywhere. So whether on your computer or a colleague's computer in the cloud. So no need to worry about different systems or settings messing up faster deployment. Docker containers are smaller and more efficient than virtual machines, which means they start up and run faster. So getting your app up and running takes less time and consistency. So by isolating application, Docker ensures that software runs the same, regardless of where it is deployed. We have explained this already, so we are eliminating environment discrepancies. So make sure your app works the same way no matter where it is running, whether you are testing it on your own computer, staging it for a review, or launching it live for users. You won't run into surprises. And this has been a basic overview of Docker and containers. In the next lesson, we will go ahead to create a Docker file for a microservice and then build the Docker image and run the Docker container. Thank you and stay tuned. In this tutorial video, we are going to be looking at how to create or write a Docker file for our FastAPI microservice. We have already looked at what Docker and what containers are, and now the first thing we are going to do is navigate to our project folder. Yes, and we are going to create a simple microservice, which we have already done. So we're going to name it app.py. That's app.py. And in this microservice, we are going to be looking basically at a simple microservice that retains a JSON response whenever a particular route is assessed. So we can see the code here, which is basically returning a JSON response for whenever this particular endpoint is assessed. So this is a simple FastAPI microservice. The next thing we are going to do is that we are going to create our requirements text. These are basically the dependencies that are needed for this particular project. So for this particular project, we are using FastAPI and Unicorn. The next step is to basically create our virtual environment. So we are going to install the virtual environment. We've already been through this. We install the virtual environment, and then after this is done, we activate it. So we are creating a virtual environment. We are naming it myenv. Alright, so when this is done, we just activate it. Alright, so now that we are in a virtual environment, we are going to install the dependencies FastAPI and then a Unicorn. Now we can go ahead to create a Docker file. So the Docker file has no extensions, so we just create it with this particular name. Alright, so the first thing that we are going to do is that we are going to use our from command, and this specifies the base image that you are going to use for your container. So in this Docker file, we are going to use the slim version of Python 3.10, and the next thing you do is we are going to set our environment variables. We are going to set our environment variables. So the environment variables are two. So the first one prevents Python from generating those .pyc files, and these are not necessary in a Docker environment. And the second one forces the standard output and the standard error streams to be unbuffed. So what this means is that it allows you to see your log output in real time. Now, with the next step, we are looking at setting the working directory for our container that will be in this particular folder. And then all subsequent commands will be run from this directory. And the next one that we are going to do is that we are going to use copy command. We are going to copy our requirement text file to the container at the working directory. So we are going to copy this requirement text, which we have created in our project folder. So we're going to copy it into our working directory. And the next thing we're going to do is that we're going to install the dependencies. So we have two dependencies for this particular microservice, which is FastAPI and Unicorn. And the command run will install the dependencies specified in the requirement text. And then the -no cache dir option is used to prevent pip from cutting the downloaded packages. So this is basically to reduce your image size. It's saying people should not use a catch when downloading or when installing packages. And the next thing we are going to do is we are going to use the copy command again to copy the application code into the container. So we are copying it into the container. And the next thing we are going to do is define the port on which the API is going to run. So we are telling Docker that the container listens on port 8000, and this is the default for port FastAPI uses when running with Unicorn. And then the last thing we are going to do is that we are going to specify the command to run the FastAPI application. So because we use Unicorn to start the application, we are going to basically be using Unicorn to start the application. Yeah, so basically the cmd command or instruction is important because it tells Docker where the main process of the container should be. So in this example, the cmd instruction is telling Docker to run Unicorn with this specific argument. So the first part tells Unicorn where to find your FastAPI. The first app there refers to the file name of the Python file. The first app there refers to the file name of the Python file, which is app.py. So you just use the file name with the extension .py. And the second app here refers to the application instance created within the file. You remember app was used to initialize the FastAPI instance. The second app there refers to the name of the instance, which is app. The next argument basically requires the host option. It requires Unicorn to specify which host or IP address the server should listen to. It basically tells Unicorn the IP address the server should listen to. And the next argument is the special address that means all available network interfaces on the machine. So it makes the application accessible not only from your local host, but also from external machines. So if you use this, the app will be accessible from within the container itself. So it means that you can use other devices or other networks. Other users on the network can also access the app using the host machine's IP address. And the last and the port arguments here specify the port that the Unicorn listens on, which we have already talked about. So that is about creating a simple Docker file for our microservice. So that is that about creating a simple Docker file for our microservices. In summary, we created our first API application, then our requirements text, and then we wrote our Docker file. And the first thing is that we specified the base image. We declared the environment variable, set the working directory, then copy the requirements for that application into our working directory. And then we stored dependencies, and then we copied the FastAPI code into the container, and we copied it into our working directory also. And then we exposed the port on which the API or the application will run, and then the command to run the first application. And this is time we are using Unicorn. And this time we are using Unicorn. All right, thank you very much. So in our next video, we will be looking at how to build and run our Docker container. So in our next video, we will be looking at how to build and run our Docker container or Docker image. Welcome to this tutorial on creating or building and running your Docker image. So the first thing you have to do is that we have to ensure that our Docker desktop is installed. Otherwise, we will not be able to build our Docker image. Because the Docker desktop is a prerequisite, because the Docker Because the Docker desktop is a prerequisite for running images and building containers using Docker. So you just go ahead to the site, which is this website, and then you download Docker Desktop. So you just click the download button, and then when it's downloaded, you go to the installer in your download folder and just click on the installer. So the installer starts running. So when your installer is done, then you can open your Docker desktop and make sure that your engine is up and running. And then we have the images here, and we have the containers here. So when we create it, you'll be seeing it here in real time. So we want to go ahead to verify if our Docker is running. So we just go to our studio code and we type in here Docker and then version. And this shows us our Docker version and build. Another way to also check if Docker is running is Docker and then info. So this gives us basically information about our Docker from our Docker desktop. So we see information here. So now we can go ahead to building our Docker image. So what we're going to do is that we're going to use a particular code to run this, and that is the Docker build. So this is the command that tells Docker to create an image from a Docker file located in the current directory, or in the project directory. So the first flag C is used to tag the image with a name. In this case, the image is being tagged with my FastAPI app. So this is basically for reference sake, especially when you are going to run the container and then the period at the end basically specifies the build context. So you are basically specifying the directory you are going to use and what the period represents. Cut and what the period represents. That means you are using the current directory. So Docker will look for a Docker file in this directory and use it to build the image. So you must always ensure that your Docker file is in the directory. Cut. So you must always ensure that your Docker file is in the directory that you are going to build your image from. So in summary, this command builds a Docker image named MyFastAPI app, using the Docker file located in the current directory. Alright, so we run this and we see that our image has been created. One other thing is to also always ensure that all your files are saved before building the Docker image. So the next thing to do now is that we want to run our Docker image. I want to create a container from our Docker image and run. So we're basically going to use this code. So for this code, the command is used to run a container based on the MyFastAPI app image we created, which is MyFastAPI app. And the Docker run is used to create and start a new container from the Docker image. And the D flag runs the container in detachment, meaning that it runs in the background instead of copying. Cut. Meaning that it runs in the background instead of occupying or having it occupy your terminal. And then the name flag option assigns a name, in this case, MyFastAPI, to the running container, making it easier to reference in future command. And then we have the P flag, which maps the port 8000 on your host machine to that to port 8000 in the container. So it allows you to basically access the FastAPI application running in the container via the local host 8000 on your machine. The last thing is the MyFastAPI app, which is the name of the Docker image. So in summary, this command runs a container named MyFastAPI in the background with port 8000 on your machine, mapped to port 8000 inside a computer using the MyFastAPI image. So now we are done. We will just enter this. So our container is up and running now. And you can check this from our Docker desktop. So we see the image which we created here, MyFastAPI app. That's our created image. And then we can see the container which we created. Now we can access our application or local host here. We just click this and then it opens our application and you see the JSON response here. So this is how to build and how to run a Docker image for your FastAPI or a simple microservice or simple FastAPI microservice. Thank you. Welcome to this tutorial video on configuring environment variables in Docker. In this video, we'll learn how to use environment variables to make Dockerized microservices more flexible and secure. Alright, so what are environment variables and why are they important? Environment variables allow you to pass configuration options, such as database credentials or even API keys, into your container, without hard coding them into your application. So this makes the microservice more portable and secure. So what it means is that the environment variables help to pass certain key configurations into our container. On our screen here, we see an example Docker file showing the env command. In this Docker file, we see two environment variables, and the first is Python do not write by the code and Python buffered. Now, I've already explained what these variables mean. Sorry, Python unbuffered, rather. So, Python do not write by to code is an environment variable which prevents Python from writing those .pyc files to the disk, so that when Python runs and it compiles py files into .pyc files, which are stored in the py cache folder. These pyc files help speed up future execution. Because Python doesn't need to recompile the code unless the original .py file changes, so by setting it to 1, Python skips the creation of pyc files, and this is useful in containerized environment. And we know, so in a case where a development of production environment, where writing unnecessary files to the disk is undesirable. This environment variable comes in handy, and Python unbuffered is equal to 1, forces Python to output open statement and logs directly to the terminal. Yeah, so it means that Python immediately writes all output to the terminal without buffering, and this is useful for real-time logs in Docker containers. Alright, so these are both useful in containerized environments for performance and cleanliness. So that is one way of passing environment variables in your Docker file. And then there's an alternative with which you can pass environment variables when you run your container, which allows for more flexibility. And then this is how you do that. We use this particular command, and the E flag here is used to pass the environment variables when running the container. So in this case, we are passing app_env equals production. And this method allows you to change environment variables without modifying your Docker file. So basically, this is another way to pass environment variables into your container, making it accessible in the container. So you can go ahead and run this and see what happens. Okay, so we got the image name wrong. This should run our Docker container with this environment variable. Another way to pass or to store environment variables is using a file named .env file. And this is for the docker-compose.yml setup. So for a project with multiple environment variables, it's more convenient to store them in an env file, so you can load this into your container using Docker Compose. So we just create a new file here, and we can add the two or any of the environment variables. Alright, so this is how we pass the environment variables. So then we go ahead to our Docker Compose file. So we save this and go to our Docker Compose file, and we can enter environment variables. So here, instead of this, we can just do input env_file and type .env. So we save this, and then we can run our docker-compose. So we input docker-compose up and hit enter. So we've passed our environment variables. Alright, so that's the end of this tutorial. So we've learned how to configure environment variables in Docker from the Docker file to passing it through the -e flag in the terminal, and then using the .env file. And then using the .env file. Thank you and stay tuned. Hello and welcome to this tutorial. So today, we are going to walk through building a simple RESTful API for synchronous communication between two microservices. And so we are going to use a FastAPI, which makes it easy to set up and manage RESTful APIs. So in this tutorial, we have two microservices, Service A, which is the client, and Service B, which is the server. Service A makes a synchronous request to another microservice to get data. That is Service B. And Service B receives a request and processes it, and returns a response to Service A. So let's get started. We are going to look at Service B. First, Service B is our server.py, and then we are going to import our modules. So our imports are two, FastAPI and Pedantic. FastAPI provides a tool to create and run a RESTful API, and then our base model is from Pedantic, which helps define the structure and validation for data models. So we initialize the API instance, app, which represents a microservice, and then the class item defines a data model with attribute ID, name, and description. Each attribute is typed, making validation easier. And we have our endpoint here, which is a get endpoint at the items/item_ID route, where item_ID is a URL where item_ID is a URL path parameter. And then anytime a GET request is made to this endpoint, the asynchronous function read_item takes the item_ID as an integer. And then what it does is that it creates an instance of the item with the provided item_ID, which serves as our response object. Now the function is defined asynchronously to improve performance. So REST simply means representational state transfer, and it allows the system to securely exchange information over the internet. Just to clarify that. Now let's go to our Service A, which is our client.py. So here are our imports Here our imports are FastAPI for building the API, and then we have HTTPX for making HTTP request from the client service to another service. HTTPX supports asynchronous request, which is perfect for microservices. So we initialize or create the client's microservice, and we define a get endpoint at /fetch-item/item_ID / where item_ID is a path parameter, and anytime a GET request is made to this particular endpoint, the asynchronous function fetchItem is called. And for this function, the first thing is that it defines our URL, a specific URL for our Service B. So what it means is we are going to run our Service B on the port 8001. Remember, our Service B is server.py, and we are on Service A, which is our client.py. So basically, we use HTTP to send an asynchronous GET request to Service B. And then, so this sends a GET request to the specified URL and waits for the response. And the received response data from Service B is converted to JSON, and that's returned directly by Service A to its own client. Now what we are going to do is that we are going to install the dependencies. We're going to use pip install. So we are using FastAPI as well as HTTPX and Unicorn. So we hit enter. Alright, so now we are going to run Service B. So when we go to Service B, we see that it is supposed to be on localhost :8001. And so right now we are going to use Unicorn to run our server.py. Make sure to expose it on port 8001 as defined in your client.py. So our server.py is up. So we are going to open another terminal and run our client.py. So for client.py, we're going to run it port 8000. So we are going to check this out using our Swagger UI. We go to the URL localhost :8000/docs, and we are going to try it out. So click try it out, enter item as 1 and execute. we should see this response, which will be the same response for our server.py. So we can try localhost :8001, and we also try it out. Input 1 and execute. You should see the same response here. So it means that service B is communicating restfully with our service A. So this is an example of a synchronous communication using RESTful APIs for two microservices. In our next tutorial, we will be looking at communication asynchronously between two microservices using message queues, specifically RabbitMQ. Thank you. Welcome to this tutorial video. So, in this tutorial, I'll be setting up asynchronous communication between two Python FastAPI microservices using RabbitMQ. So what is RabbitMQ? Well, RabbitMQ is an open source broker software that allows applications to communicate and exchange data. So it basically acts as a mediator between message producers and consumers. So it manages routing, queuing, and delivery of messages. And this is a popular choice for building real-time application because it's reliable, scalable, flexible. In our previous tutorial, we looked at synchronous communication between two FastAPI microservices using RESTful APIs. So here, we are going to go into using RabbitMQ. So we have to install some dependencies. So I'll just move into my virtual environment. And the next thing that we are going to do is, like I said earlier, we are going to install dependencies. So basically, we are installing Uvicorn. We are installing Pika. We are installing FastAPI. Now, what is Pika? Pika is basically a protocol for RabbitMQ. So we start to install these dependencies. So we installed Uvicorn already. So you install Pika. You can actually install all with one line of code. So now we want to move ahead into make to setting up RabbitMQ. So we are going to run our RabbitMQ container using a RabbitMQ image pulled from Docker Hub. So we'll just clear the terminal. So we'll use this code to run our container. So this the last argument here, RabbitMG3:management, is the Docker image, and the port 15672 is for HTTP management UI. And then we have 5670, which is for AMQP protocol port. So they are both ports, two different ports, serving different purposes on which RabbitMQ is going to be exposed on. And some rabbit here is the name of the container, and we have the host name here. So we hit enter, and we see our container has been created and is running. So the next thing we are going to do is to create our producer.py. So this is the code here. And the producer.py will send a message to RabbitMQ whenever a request is made. So we import the necessary dependencies, FastAPI, and then Pika. So the next thing is our app initialization, and then we have our RabbitMQ setup. So the first thing here is that we see the RabbitMQ_host. And we see here that the RabbitMQ_host is going to be using our local host. If our app was being deployed on Kubernetes, we will probably use the name in the cluster or in the cluster IP to replace the local host, because it will be internally assessed. Because it will be internally accessed. And then the RabbitMQ_queue is the queue that we are creating for our connection. Also, the connection in line 11 connects RabbitMQ on our local host, and then opens a channel to communicate, and we see the queue declaration, which ensures the queue RabbitMQ_queue exists. And then the durable equals true, make sure that the queue survives whenever RabbitMQ restarts the queue still survives. Now we look at our API endpoint, which is a post method using a post method and then the /send route. So basically, the post endpoint takes a message parameter and sends the message to RabbitMQ_queue and confirms that the message was sent. So it means that whenever this endpoint is assessed, a message is going to be posted to the server and the message is sent to RabbitMQ_Q. And then we see that after the message is sent, there's a confirmation that the message has been or the message was sent. So this channel.basic_publish we see here does all that and returns a confirmation that our message has been sent. The return function posts the message status, message sent, and then the value of the message key was posted to the /send endpoint. Now we are going to run this producer service. We want to run the producer.py using Unicorn, and we will expose it on port 8001. So we quickly move to our customer service. It's rather consumer.py. We create a file named consumer.py and add the following code. So we are going to explain the code quickly. So we have our imports, we have our initialization, and we have our RabbitMQ setup as the previous one. And then we have the callback function. For the callback function, its purpose is that it is called whenever a message is received, and prints and acknowledges the message. So it prints and acknowledges the message. The next thing is the start_consuming. Cut. The next thing is the start_consuming function. It connects to RabbitMQ using the same connection, and then it opens a channel. It ensures that the same RabbitMQ_Q exists. So it ensures that the RabbitMQ_Q exists, which is the queue we have declared earlier. And then the prefetch_count equals 1 ensures the consumer processes one message at a time. And RabbitMQ starts consuming messages with the callback function. The next one is the startup event. We are saying that the consumer should be started in a separate trade when the FastAPI starts. And then the daemon equals true ensures that the thread closes whenever the program exists. Another thing is the health check endpoint. So we open another terminal. Always have to make sure that you're in the directory containing the file consumer.py. Then we run this also. Alright, so we are going to basically test this using our web browser and then the FastAPI documentations. So we are going to check this using Swagger UI. So what we are going to do now is to try this out. So basically what we are doing is that we are sending a message or we are sending a post request to producer.py's /endpoint. Cut. Or we are sending a post request to producer.py's /send endpoint. So let's just type hello RabbitMQ. So we, after doing this, we just execute. So we see our response here. The message sent is hello RabbitMQ. So we are going to look at the terminal running our consumer py. So we are going to look at our logos in consumer.py to check if the message was sent asynchronously. So we see here received message hello RabbitMQ in our consumer.py logs or our customer.py output. So basically, this is a tutorial video on how to send message asynchronously. Asynchronously means that you don't need an immediate response, like what we did last time with the RESTful APIs, meaning that once you send a message, you have to get a response there and then. But this does it in the background. So in our next tutorial video, we'll be looking at another way in which microservices can communicate or send data between themselves using the gRPC. Alright, so welcome to this tutorial video on gRPC for communication between two FastAPI microservices. So in this video, we'll cover the essentials of gRPC, how to integrate into FastAPI, and efficiently set up communication between two microservices. So before we dive into the code, you have to understand what gRPC is. Well, gRPC means Google Remote Procedure Call, and it is a high-performance open-source RPC framework initially developed by Google. It is widely used for connecting distributed systems. When we compare it to REST, we find out that gRPC has efficient binary communication via protocol buffers. It has built-in support for multiple languages and is highly efficient, making it perfect for low-latency use cases. Alright, so that is an introduction to what RPC is and why we use it. So the first thing that we're going to do is set up our environment. So we have to install our dependencies. So we're going to install dependencies right away. We install FastAPI, Unicorn, gRPCIO, gRPCIO tools, and protobuf. Yeah, so protobuf is to define our data model and service contract. gRPC, gRPCIO, and gRPCIO tools are needed to work with gRPC in Python, and FastAPI is to handle the microservice framework. So we're just going to install this right away, hit enter. So all dependencies cut. Now all dependencies are installed. So we start by first defining our proto file for our protocol buffers. We define them in our .proto file. This file describes the service and data structure. So we see our code here. Firstly, the syntax equals proto3 specifies that we are using protocol buffer version 3, which is simpler and more efficient than 2. For the service data transfer, this defines a gRPC service called data transfer that contains one RPC method. The RPC method here is send data. Alright, so send data is a remote procedure call that accepts a data request and returns a data response. And we have our data request, cut, and we have our message data request and our message data response. So this defines the structure of the request and the response message. In this case, the request message contains a string message. The data response contains a string status equals 1. So we want to generate the code from the proto. Cut. So we want to generate the code from the proto file. So we need to generate the Python classes for gRPC and messages, service and messages using the gRPCIO tools. So we are going to generate the Python codes from this file here, the proto file. Alright, so we run the following command. So the -i flag here tells proto where to find the .proto file, which is in our current directory. That's the reason for the single period. The Python_out generates the Python code for the protocol buffers, and the gRPC Python generates the gRPC server and client code. So we are going to generate two files, service_pb2py, which contains the message classes, data request and data response, and then service_bp2_grpc.py, which contains the gRPC service definitions. So we are going to run this code here. Okay, so I think we have saved our auto file and we run it again and we see that our Python files have been generated. So now I want to implement the gRPC server. So let's implement the server in one of our microservices, which is server.py. So the data transfer service, closed brackets, is also called. So this implements the same data method defined in our .proto file, and this method receives a request and retains a data response. So here it simply prints the message received and returns it success status. Now the serve closed bracket function creates a gRPC server and registers the data transfer service. So we use a threadboard executor with a max of 10 worker threads to handle multiple requests concurrently, and then the FastAPI integration. So we create or start the gRPC server. So we start the gRPC server when FastAPI starts. The startup event creator ensures that gRPC server is running in a separate thread. So we're talking about this code here. After the initialization, we have FastAPI integration. Yeah, so we are saying on startup that the gRPC server should run in different threads. So I think that about explains the code. So like I said, the data transfer service class implements the send data method that we had in our service.proto file. Alright, so we're going ahead to run our server. We hit enter. Alright, so in the second microservice, we set up gRPC client to send data to the server. A gRPC client function creates a gRPC client, create connection to the A gRPC client function creates a gRPC client, create connects it to the gRPC server, add localhost :5051. which creates a data request message and sends it to using the sendData method. It returns the status from the server. The FastAPI will send data, accept a message from the client, and send it to the gRPC server using gRPC client. It returns the service response in JSON format. So we run the client.py by using another instance of Unicorn. Alright, so we are going to test this out in our web browser using the Swagger UI or FastAPI documentation. So just move straight to the web browser and then you are going to input 800 localhost /8001 /docs and you should see your endpoint. So this here is our client service. So we send hello world from our client service and execute. We see the response here is success, and we check our logos. So cut, and we check our logs. So in our client service, you see that a post method has been used to send a request to the /send-data /endpoint. And we'll see the response if we check for the response in our server.py, and we see that it has received a message. In summary, we have learned how to transfer data from one microservice to another using gRPC method. We learned how to define a .proto file, generate the Python files from it, and then use it for communication between two microservices. Thank you. Welcome to this tutorial on managing states and data persistence. So, in this set of tutorials, we are going to be looking at databases and adding databases to our microservices. So for this, we are going to download and install PostgreSQL locally. There are other forms of databases which can be connected to your microservices, either on cloud, using GCP Cloud or AWS Cloud, etc. But we are going to be using PostgreSQL. So there's PostgreSQL, there's no SQL, and so on. But this will be the local database we're using for our microservices. And in this tutorial, we'll be setting it up, and in the subsequent ones, we'll be showing how to connect it to your microservices. You can apply the concept with other databases. So in this one, we are going to download version 17 from this website. Select for Windows and click Download. It takes you to a new page and your download starts. So we are going to go and click on the downloaded installer and start the installation process. You click Next, and you click Next, and then Next. And so we come to a point where you have to input password. For this password, you have to remember because you will be using it every time. You are going to access your database as the default user Postgres. So we are going to use password as the password and click Next. And this is the port is going to be exposed on 5432. You click Next and then the default local. So you maintain this and click Next, and then you click Next and then it begins to install. Once it's installed, you'll be shown Stack Builder. With this, you can just click Finish and then you can close this straight away because you don't need to install any other programs. You can if you want to, but it's not necessary to do any other installation. So you can just finish your installation process. So we are going to go to our desktop, or you go to your Start folder, and you should see pgadmin as one of the applications that have been installed. Open it, and you click on the service. You should see Postgres. Right now, we have actually put our password for Postgres, which is our default user. So we enter password. Our database is shown here. So we see our databases, login roles, and table spaces. So this is an administrator for our Postgres So this is an administrator for our PostgreSQL database. So this is an administrator for our PostgreSQL database. Now, I want to make sure that we can access the database through our command line at any point on our system. So we are going to basically go to where our psql.exe is located, which is located in the bin folder of our Postgres installation folder. So we see the file psql.exe, and we just copy the directory, And then you go to your environment variables under Advanced System Manager and go to Path and click Path. Click Edit, and then you're going to add a new variable. You are going to paste that directory for PSQL, which is our command line tool for our database. And now you open a PowerShell and you type PSQL-U Postgres, which is our default username, single S, and then you're asked for password. So here you are supposed to impute the password that was used during the installation. We made a mistake, so we're going to run the code again and include the password again. So we enter our password, and now we are in our database as user Postgres. We are in our database command line, and now we can create tables using SQL. We just type create database here, all caps, and then you write the name of the database, which is db_sample, and hit enter. So we are supposed to add the colon, cut. So we are supposed to add the semicolon in SQL syntax. So we do it again, and our database has been created. You can verify if it has been created by using \c db_sample and hit enter. What it means is that we are connected to our database. We are connected to our db_sample database as user Postgres. And then we can create tables using create table users, as we see here. You can insert also into our tables, as we see here. So this is basically SQL syntax, something that you must or you should be conversant with when assessing data from your database. We'll go into it more in our next tutorial using the Python and our microservice to create data and add it to our databases. But for now, this is just a tutorial on how to set up a database locally so that we can connect it for managing state and database systems for microservices. So thank you very much. In our next tutorial video, we will be looking at connecting your microservice to a database. Thank you. Alright, so welcome to this tutorial video on connecting a simple FastAPI microservice to a PostgreSQL database. So we are going to be using SQL Alchemy to communicate with our database. Alright, so the first thing we have to do is that we have to log in to our PostgreSQL database. So just use this code. So when we run this code, we are asking for our password, which is the password you used during installation. You are always supposed to remember the password used installing your PostgreSQL database. So password is what we used. So now we can create a database. So we just type create database user_db, and our database has been created. Alright, so we can check the list of databases. Okay, alright, so we can see our user_db here. Okay, so we are going to exit from this using \q. Alright, so now we can go ahead to connecting our FastAPI microservice to our database we just created. Alright, so we install our dependencies FastAPI for our microservice framework and SQL Alchemy to communicate with our database or interact with our database, which is an ornament. And then psycorpg2, cut, and then psycorpg2 is a PostgreSQL driver to connect Python with PostgreSQL. So hit enter to install all the dependencies. Alright, so our dependencies have been installed. Now we look into the coding. So we import the following libraries and modules, and then we initialize our FastAPI application, and then we have our database configuration, which sets the database connection URL, and this URL includes the database type, which is PostgreSQL, the username. Our username is Postgres, which is the default username after installation, and our password is password. And then you have your host, which is a local host. You have the database name, which is user_db, and then we create an engine that allows SQLA cut, And then we create an engine that allows SQL Alchemy to interact with PostgreSQL database using the connection string provided in our database URL. And then we create a session class to handle database transaction. So each session would interact with the database engine and will commit or flash changes automatically, will not commit or flash changes automatically. And the next step is defining the database model. So the base serves as the foundation for creating database models. That's the tables. And any class inherited from base will be treated as a database model. So this is the definition here. So we have an ID, which is an integer name string, and an email, which is a unique string field, which ensures that each email is unique. And then we have a pedantic schema for input validation. So this is to validate that the type that is being received from the user is the same type as defined in this pedantic model. And we have the dependency to get a database session. So this creates a database for each request using the session object DB, and ensuring that the session is closed after the request is processed. This is used as a dependency in routes to access the database. And here we have a post request to /users, route which will trigger the function getUser. To trigger the function createUser. And this function makes the user data validated via userCreate schema and the database session DB. So it creates the user object basically and adds it to a session, commits a transaction, saves it to the database, and returns the newly created user. Alright, so we have the next route, which uses the getRequestToUsers and the user ID. So it retrieves the user with a given ID, and the function getUser looks for a user with a specified in the database. If no user is found, it raises a 404 user not found error. And we have the last part, which runs the first API using Uvicorn. So now we can run this. Because we have Uvicorn already defined in the file, then once we run Python and then the name of the file, which is user.py, hit enter. Our app is running. So now we want to test this connection. So go to our browser and check localhost :8000 when you use that documentation. Right, so we have a post and we have our get function here. So we want to try the post out. So try it out. So we're going to enter a name, John Knox, and email johnknox@gmail.com. We then execute this and we see the server response code 200. These are name and these are email. So successful response. So we can try another one. So let's try maybe John Daniels. Click execute. We see here that the two are successful. So I want to check our database, if those tables have been created. Alright, so basically use this. Enter our password and then we are going to connect to our database. So enter /c and user_db and then check the table /dt. So we can see our users have been created as a table name. So now I want to see the content of users. So I'm going to select all from users. Hit enter. Select all from users. We have to put our colon. Yeah, so we see John Knox and John Daniel. So this means that FastAPI application has been connected to our PostgreSQL database. Alright. And you can also test using the get method and the users /user_ID. So you can try it out. We type 2 and then click execute. So we see number 2 is John Daniels. Alright, so that brings us to the end of this tutorial. So in our next video, we'll be looking at implementing database per service pattern. Thank you and stay tuned. Welcome once again to another tutorial. And in this video, we're going to be looking at implementing the database per service pattern with FastAPI and PostgreSQL. So we looked at connecting one microservice, a FastAPI microservice, to a database, specifically to a database called user_db. And then we created a table called users, which includes the usernames and their respective emails. So in this video, we are going to look at adding another service, which is order.py, and creating a separate database, which is order_db. and creating a table in this other database called orders. So the user-service is going to manage users with its own PostgreSQL database, and then the order service will manage others with a separate PostgreSQL database. So each service will have its own database, scheme, routes, and isolated responsibilities. So this pattern ensures that each microservice manages its own data and database, keeping the services decoupled and allowing them to evolve independently. Alright, so we've already installed our dependencies, so we just run through our code, which is our order-service.py. So similar to our user service, we import modules, we initialize the FastAPI application, and we set up our database connection. So our username, once again, is Postgres, unless of course you have changed your username, but this is the default username that is given upon installation. And my password is simply password, and host is localhost. And then the database name is order_db. We've been through most of this in the user-service. So we set up an engine for the database using the database URL, and then we create a session local order. We are saying that it should not auto-commit or auto-flush, and it should run on the order_engine created. Earlier, we said that the base order is the declarative base, which is basically the model which we are going to use for our tables. We have our ID, user ID, and then we have the item name. So the ID is integer, user_ID is an integer, and then we have our item name. And we have a pedantic schema for order-service, which is ID, user_ID, and the item name. And then we have a dependency to get to our order-service DB session, and it returns DB and it closes when the session is over. The first endpoint basically posts order to the orders route here, so it creates order. So you see that anytime a post request is made, this function is called create_order, which basically creates an order and then stores in database. So it creates an order and stores it in a database. And then the next endpoint, which is a get endpoint. This receives information based on the particular user order_ID, and it is stored. So it requests information from the server using a particular user_ID. So it searches through the database to find out if the order exists. If it does not exist, it raises an exception for order not found. And this here creates the database and runs the order-service. So we just save this. Always you make sure that your virtual environment is created and activated. The next thing you're going to do is to create the tables using this code. Postgres is the username. So Postgres is the username. Cut. So Postgres is the username. The password is password. And then we are going to create database. Create database order_db. Alright, so we have created this database. We can check this by using \1. So we see order_db there. Now user_db as well. So we exit \q, and now we are going to run our Python order.py again. So we can check the link out. We can just press Ctrl and click the link. So we'll check using FastAPI documentation or Swagger UI. Alright, so we can create an order here. So let's create an order. Let's try it out. User_ID equals 1 and item_name is a laptop. Click execute. We can try another one. User_ID equals 2. Item_name equals school_bag. So we can check with our get endpoint. Try it out. Enter 1 and execute. We see the item laptop. We can also check our database. Cut. We can also check our database manually using psql-u Postgres. Password is still password. Cut. Password is still password. We are going to connect to our order_db and then we can show our table. So we type select star from orders, which is the table name. So we have laptop appearing. I guess if I executed it twice. So yeah, so this is our user_ID and our item_name. So this basically means that we have two microservices, our order service and our user service, and we have two different databases for both. So this brings us to the end of this tutorial. So in our next tutorial video, we'll be looking at using Redis for caching for performance optimization. Thank you. Okay, so welcome to this tutorial on using caching for performance optimization with Redis in Python Microservices. So in this tutorial, I'm going to demonstrate how to integrate Redis caching into a FastAPI microservice to improve performance. So caching helps to reduce database load and improve response time by storing frequently requested data in a fast memory store, which is Redis, rather than repeatedly querying the database. So what it means is that caching is basically a technique used to store frequently accessed data in a faster storage location. So it means that you do the time it takes to retrieve data. So instead of always querying the database, an application can check the cache first. So it gives improved performance and reduces the load on databases. Now, Redis is a remote dictionary server, which means that it's a memory data store, often used as a caching layer. So it supports various data types, including string, lists, and so on. So we'll go into our tutorial for today on using Redis for caching a microservice. So now we are going to create a simple product service. I want to create a simple asset that connects to a PostgreSQL database to retrieve product information. And we will use Redis cache to store the product data, optimizing the retrieval of product details. So the product service will cache product information in Redis when it is first requested, and subsequent requests for the same product will be retrieved from the cache instead of the database. So we navigate to our project folder and create a new file called product.py, which is product service. Now what we'll do is we will install all our required packages. I have all of our packages installed apart from Redis. So for Redis, we type pip install Redis. Hit enter and it will be installed. Now we are going to run Redis locally using Docker. We are basically going to run our Redis because we don't have Redis image locally. So it's going to pull the Redis image and run the container. So our Redis is running locally on Docker. Yes, so we can check our Docker desktop and we can see that Redis is running. Alright, so we go to our product service.py and import the necessary modules. And just like what we did in connecting to our database tutorial, we set up the FastAPI. We connect to the database, we have our database username and the password, the engine created, and the model as well. So now we will move straight to setting up the Redis connection. So a Redis_client is created to connect locally running Redis on the machine. This will be used to cache the product data. And we can see that there's a caching attached to our getProduct endpoint. The get_product endpoint function first checks whether the request product is cached in Redis, if it's found. The cached one is then retained. If not, the product is fetched from the database and the result is cached in Redis for future requests. And that's what we have here now. We are essentially saying that if the product is cached, then it returns. So the function checks whether the request is cached. Cut. So the function checks whether the request is cached. Then it returns the product if it is cached. But if it is not cached, then it is fetched from a database. So if it is cached, it returns the product. If not, it returns from the database. Then after it returns from the database, it is cached in the Redis for future requests. So the /products/endpoint has no caching involved. and this endpoint allows us to create a new product in the PostgreSQL database. So caching is not used since new products are stored directly in the database. So we run the service with this particular code, and I want to run the service right now. But before we do that, we need to create a table for our database. So we're just going to use psql-u Postgres, and our password is password. I'm now going to create database product_db. Product_db is our database name. And now we have created a database. You can now just exit from the PostgreSQL with \q. We clear this, so now we can run Python products.py. Alright, so copy this link and go to our browser cut. Alright, so copy this link and go to our browser at /docs. But first we have to create the product. Click try it out. Product_name equals laptop and price equals 900. And then school bag and price equals 90. Then we click execute. So we want to check our get endpoint. We can try this out with ID equals 1, and then we execute laptop cut, and we can see that laptop and price is 900. This means that this has been cached in our Redis. So what it means that if we are to execute this again, it is supposed to return from the cache, not from our database. We can check our Redis cache by using this code right here and entering it into our Redis command line, because we are running it locally. Then we can check if a particular key exists. And so we will check if a particular key exists. We hit enter, and we can see that this particular key does exist. And now we want to get the particular value for that key. So we use this code, and we see that the ID with no equals 1 has name equals laptop and price is now stored in your Redis cache. This has been talking cut. So this basically has been about using Redis caching for optimization or the performance of our microservice. We can exit from here. Just type exit. And that's about all about Redis. Thank you and stay tuned. Welcome to this tutorial on implementing authorization and authentication for a simple FastAPI microservice. In this tutorial, I'm going to be using a local PostgreSQL database for storing user data. Essentially, we're using pedantic models and SQL alchemy to interact with our PostgreSQL database. Because of this, we are going to have 5 different files. We are going to have our crud.py, which basically are operations for the database, that is create, read, update, and delete. And then we have our database.py, which establishes the database connection. We also have our models, that is the pedantic models. And then we have our schema for how the database is going to be organized, how the tables in the database are going to be structured. Now we'll go to our main.py. However, before we do this, we need to explain the difference between authentication and authorization. Authentication basically verifies the identity of a user or a service, and authorization determines their access rights as what the user or service is able to do or not do. Now we are going to go into main.py code. And the first thing is to import our libraries and modules. We know that FastAPI is a framework that creates the web application. And we have SQL alchemy that helps us interact with PostgreSQL database. And we also have pedantic, which validates the data we receive in a structured way. Then we have parse lib. Then we have parse lib, this handles password hashing, which essentially means it secures the password by converting it into a scrambled version. We also have JWT, meaning that we are going to use JSON web tokens to generate tokens for user authentication. We have data time and time delta, which are used to manage token expiration time. And we have CRUD, which we mentioned earlier for creating, reading, updating, and deleting. And it's used for database operations and soget_db. This helps us interact with the database by getting connection to the session. So we are now importing our models, CRUD, schemas, which are all in our project directory. So line 11 here ensures that the database tables are defined in the models. PY are created in PostgreSQL. It sets up a structure for the user's table where we store username and hashed password. The next thing we do is that we initialize our application. Here we have our JSON web token configuration. So the secret underscore key is a secret string used to verify the JWTs. Think of it like a password for generating secure tokens. That's the secret key. And the algorithm is the method used to encrypt the token. So HS256 is a common algorithm. And the access underscore token underscore expire underscore minutes tells us how long the user's token is valid. In this case, we have 13 minutes. So we have two functions here. The create underscore access underscore token function creates a token with the user's username. And then the get underscore current underscore user verifies the current underscore cut verifies the current user underscore based verifies the current user based on the token. So the function decodes the token and retrieves the user based on the token's data. And they have a third function also, which is the get underscore admin underscore user. This checks the role of the user, allowing only admins to access certain routes. So okay, let me go over it again. So we have three functions. This creates the token based on the username. This verifies the token, and then this checks if the current user is an admin. It essentially checks the role of the user. If it is an admin, it is given certain privileges. So this is for authorization, and these two are for authentication. And now we see the root. So the /create underscore user / endpoint is the route that we are going to use to generate a token. This route creates new users. It's a public route, and this is an admin route, which deletes users. The code is basically saying you create a user with a username and password, and then you log in to get a token. And if the token is correct, or if your username and password is in the database, you are authenticated and you are allowed to access the token. But you can only delete users if you are an admin. That's essentially what the code does. And then we have our CRUD, which essentially defines the database operation, the get underscore user, the create underscore user, the delete underscore user, the hash underscore password, and the verify underscore password. We have our database connection to our database. So a database is auth underscore db. The first thing we have to do is to install dependencies. And we will install the necessary dependencies. Pip install FastAPI, Uvicorn, Python-multipart, parselib, bracket, bcrypt, close bracket, Python JOSE. The next step is that we are going to create our database. So first, we log in to Postgres, input password, then create database, auth underscore db semicolon. Now we are going to go over the other files, which is the models.py, which is a pedantic model for the user table. So we have ID, username, hashed underscore password, and then role, and then schema.py, which contains user create model. username password, and then user login model, which is username and password. So this is the model for user login, and this is model for creating a user create. They are all used in our main PY. There is a lot of coding, and you do have to go through it. But I've overall explained how it works. So we have authentication. You create a user, and then you log in. The user is authenticated. If you are a user, the token is generated, and then for the admin, they can delete. When you are creating an account, it asks for a role. Alright, so having done all of this, we're just going to run this application using Unicorn. So run the code and hit enter. Alright, so our application has been started up, so we can go ahead and use the Swagger UI for documentation. Go to our browser, go to localhost :8000/docs, so now we can create a user, which is public. You should now click try it out. Username equals John. John's password is PQRTA, and the role is user. I'm just going to create this by clicking execute. Now we have created John. I now want to create another user, James. James's password is QERTY. We are going to make him an admin. We are now going to execute this. Now we want to log in. Click try, click try this one out. Because we are using this UI, this and this is for authentication. But when we run this, you see that a token-generated token is generated in the bearer. You use this. You can use this for your command line using curl or evoke REST method. But for this one, if we don't authorize this, we cannot have access to it. So even if we try it out and use James, of course we have not been authorized. It means the token is not valid and we can't have access to it. Therefore, we see not authorized. But I now want to authenticate it. So we input James, and then the password is QWERTY, and then this is string. Click authorize. So it means that we are authorized now. We can go to execute this or delete a user. We are going to delete John, which was a user created, and we can now click execute. We can see that user John has been deleted successfully. So we created two accounts. We created John, which is a user, and James, which was an admin, and only the admins have access to delete users. We can now see this better when we pass agreements using the command line. For that, we have to have the token generated to be able to delete the user. This was essentially a tutorial of how to enable authorization, authentication, So this was a tutorial of how to enable authorization and authentication in FastAPI. Please go through the codes over again. Please go through the codes again to get a better understanding. Thank you. Hello and welcome to this tutorial on API Gateway with centralized security and using FastAPI in Docker. In this tutorial, we will build a microservice architecture using FastAPI. We will set up two microservices, Service A and Service B, and an API gateway to route requests to them. The API gateway will handle token validation to implement centralized security, and will also containerize or dockerize the whole setup and orchestrate it with Docker Compose. By the end of this tutorial, you will understand how to build microservices using FastAPI, how to implement API gateways to handle security, and how to orchestrate these services using Docker Compose. The first thing that has to be addressed is what an API gateway is. You can think of it as a gatekeeper for a group of service applications. It sits between clients like your mobile browsers and mobile apps, and the backend services, which is the routing request to write service and handling tasks like security and request filtering. So instead of interacting with multiple services directly, clients only talk to the API gateway, which commands all the complexities behind the scenes. We are going to go straight into our code. The first thing we have to do is set up a microservice. So we create 3 folders. We create your virtual environment, and we've already been through this. And then you can create the 3 folders: service_A, service_B, and then your API_gateway. The first thing we are going to look at is service_A. So for service_A, we are going to create the code main.py. This service will just have a single endpoint that returns a message. So service_A defines a route at /service-A using the @app.get decorator. This means that when a user makes a GET request to /service-A, the function read_service_A will handle it. The function will handle it and return the response from service_A. And then you have the Docker file for service_A. Here you have your base image, from, your work dir, copy to run the install packages, and then requirement.txt. So there's a requirement.txt for all services, which is FastAPI and Unicorn. Then you copy application code into the container, and then it's exposed on port 8000. We now go to service_B. We can see that service_B's main.py also has a simple get endpoint, which retains a message. So whenever a GET request is made to this route, the function read_service_B handles it and returns response from service_B. And we can see our Docker file, which is also similar to that of service A. We also have a requirement similar to that. Now we are going to go to our API_gateway code. So we open our API_gateway folder and we see our main.py. We import the necessary required libraries and FastAPI for building the API gateway. HTTPX is an HTTP client that will help us forward requests from gateway to microservices. Depends and HTTP exception of for token validation, and we create an instance. Line 9 to 11 basically defines an async function validate_token that checks whether the provided token is valid. If the token is not, the valid token encodes the function, raises the HTTP exception with a 403 status code, indicating the user is unauthorized. So, in line 14, we see that it creates a route at /API/service-A and uses the defined validate_token to ensure that every request is validated by the validate token function before proceeding. And the line 15 to 17 rather uses the HTTPX async client to forward requests to service-A using the URL. So it sends an asynchronous GET request and returns the response in JSON format. We are using service A here because we are running our service through a docker-compose. And so in the Docker Compose, we have defined service A. So line 21 creates a route at /API/service-B, working similarly to the one for service A. But this time we are forwarding the request to service B. So it's basically identical, apart from the services. They are the ones cut. It's essentially identical apart from the services. So it essentially means that this one is an API gateway endpoint to route request, and this one is an API gateway endpoint to route request. Now we are going to Dockerize our services. So I've already been through the Docker file. So we go to docker-compose.yml file, and we are going to build all the services. So we are building service A, and this here just talking about the context we're building from, and that is the folder service A. The port here, 8001:8000, maps the port on your computer to the port running on the container. And now we can run our Docker Compose. But there's also the dependency. We are saying our API_gateway depends on service A and service B, and we are going to build from a Docker file for all the services, and we specify the directories for building each service. Now we can run our Docker-Compose app. I've already built the services. So I'm sure that you see the service will be built first before the containers are created and then run. But now we want to test it. So we are going to go to our browser, or we can simply click on this link. If I want to access service A, we use this request. Essentially, we are saying that I want to access service A from the API gateway, and our token is a valid token. Our token equals valid token. So when we do this, we see message response from service A. But if I change anything, you see unauthorized, meaning that we don't have the correct token. And for service B, you see the response from service B. If you have to change this to anything else, you will see unauthorized. In this tutorial, I'll do 2 FastAPI microservices, and I've routed them through an API gate without handles token-based security. API gateways can handle authentication, which we have already covered in authorization, and you can mix it up and create something from this. This is just a basic tutorial to give you an understanding of how the gateway works. Remember, I have said that a gateway is just like a gatekeeper for a group of services. Instead of interacting with all of them, you just interact with the gateway, and the gateway does all the background work for you, like security, authorization, and so on. Thank you very much, and see you soon. Welcome to this tutorial video on setting up secure communication with HTTPS and SSL, TLS, and FastAPI, Python Microservices on Windows. So the first question is, what is HTTPS? Well, HTTPS is Hypertext Transfer Protocol Secure, which is a secure version of HTTP. The protocol valid data is sent between your browser and the website you are connected to. So that's the secure version. HTTPS ensures that the communication between your web browser and the server is encrypted and secure. It is widely used to secure sensitive data like login credentials, payment details, and other personal information. And SSL is Secure Sockets Layer, and TLS is Transport Layer Security, which are cryptographic protocols that provide secure communication over a computer network. SSL is the older protocol developed in the 1990s, and it has gone through several versions, but due to various security vulnerabilities, it has largely been replaced by TLS, which is the successor that provides stronger encryption and a more secure communication. TLS is now the standard security protocol. TLS is the standard security protocol used today. Alright, so now we are going to go to the practical aspect. First of all, we have to install our dependencies. Pip install FastAPI Unicorn. Alright, so we have installed FastAPI. The next thing to do is that we need to open SSL installed on our machine to generate SSL certificates. So now we are going to download OpenSSL. Open your browser and go to slproweb.com. Then select the .exe for Windows 64 download. When you download, you run the installer to install it. So the installation process is simple. Click Install. You can just uncheck this and finish. Now you have to add your OpenSSL to your path variable in your environment variables. Alright, so you open your advanced system settings and go to environment variables. Go to path, select path, edit, and then you're going to go to the directory in which your SSL has been installed. So you go to this PC local disk, your program files, and then go to open SSL and copy the address. Now paste it in the path variables and hit enter. Okay, so we are now going to create the certificate or generate a certificate using this command. So OpenSSL is a command line to provide SSL/STL certificate. Reg specifies that we're creating a new certificate request. X509 tells OpenSSL to generate a self-signed certificate, and then the new key RSA:4096 generates an RSA key pair of 4096 bits, and a private key will be created and installed there. The file is specified by the -keyout, which is key.pim. This specifies the file name for the private key file. In this case, it's in key.pim, and the -out flag specifies the file name for the output certificates, which is cert.pim. And then the days sets the values of the certificate to 365. We then hit enter. Okay, so now we are going to restart our Studio code because of the changes we made to the path variables. After the restart, we can run the code again. So I'm just going to type anything, like good. So you can type any 2-letter word here and give answers for the rest of the questions and give answers for the rest of the questions and hit enter. We can see that files have been created. Our files have been generated. So we go into the application. This is a simple FastAPI that returns a JSON message for the root endpoint. Here we have the function that runs the code block that runs the application, the FastAPI application. You are basically telling it to run with Unicorn the file name and the name of the instance, the host and the port. This is the key file, and this is the cert file, which we see here. Now we can run this. We are just going to run python app.py. Remember the phrase that we imputed, which is good. Now our service is running, so we can access this site on our browser. We can access this site on a browser using this URL. Because it is a self-signed certificate, it will show a security warning. We can just bypass this. And then we see our application. Alright, so this has been a simple tutorial on securing communication with HTTPS and SSL/TSS for FastAPI microservices. Thank you. Welcome to this tutorial video on the basics of Kubernetes and its role in microservices. So for this tutorial, we are going to cover Introduction to Kubernetes Architecture, the role of Kubernetes and microservices, and Kubernetes development. So we can start with the question, what is Kubernetes? Well, firstly, the shortened form of Kubernetes is K8. That means from K to S, there are 8 letters. We have Ubernet, which is 8 letters. So then, what are K8s? K8s are basically an open source container orchestration platform that automates deployment and scaling and managing and the management of applications or microservices. K8s are one of the most significant advancements in managing containers at scale, and this makes it the cornerstone of cloud-native applications. Basically, K8s provide essential services such as load balancing and scaling. It simplifies the management of containerized applications and also ensures flexibility, innovation, making it suitable for any environment from on-premise to the cloud. So with that, K8 developers can focus more on writing code rather than managing the infrastructure, thanks to its powerful automation feature. So K8 makes scaling and balancing of microservices very, very easy. So the programmer just has to think about writing the code and not how to manage the infrastructure. That means if you have a big application with numerous microservices, the programmer doesn't have to think about managing those microservices because K8s automate them for the programmer. So what is the K8 architecture? At the core of K8 architecture lies a highly efficient, scalable architecture. The control plane includes components such as API, server, etcd, which governs the cluster's operation. It ensures that the workloads are properly distributed and managed. So the control plane ensures that workloads are properly distributed and managed to avoid the system from shutting down, or one part of the system and having more workload than other parts. So it distributes the workload effectively across the systems and then the nodes. The nodes host the application workloads in containers grouped into pods, the basic execution unit in Kubernetes. So pods are the basic units and nodes host the application workloads in containers. The containers are grouped into pods, which is the basic execution unit of Kubernetes. And the architecture allows K8s to balance, scale, and monitor workloads regardless of the underlying infrastructure. But what is the role of K8s in microservices? Like we said, K8s automate service discovery and load balancing, which is crucial for enabling communication between microservices. In simple terms, we are saying that K8s help microservices. They are a small part of a bigger application. They help a small part of a bigger application find each other automatically. Imagine you are running a restaurant and you need to call the chef, the waiter, or cashier when you need them, which are basically different microservices. K8s make sure that each of them is easy to reach without you worrying about where they are. It also balances the number of tasks given to each microservice so that no microservice is overloaded. For scaling and fault tolerance, K8s support scaling at microservice level, making it easier to manage growing applications. So, as the app grows or the service grows more, just like more customers come into the restaurant, K8s can automatically add more workers, that is, more microservices to handle the load. If one of those workers fails or stops working, K8s replace it quickly, ensuring the service keeps running smoothly. And this helps apps handle more traffic and prevents crashes from affecting the overall system. Lastly, we'll go into the deployment of Kubernetes. This specifies how many replicas of a microservice to run and the container image to use. It manages replica self-scaling and self-healing capabilities of microservices. The pods are the smallest deployable units in K8, containing one or more containers. So K8s ensure the correct number of repairs for fault tolerance and high availability. So deploying microservices on KIDs is straightforward, thanks to the deployment object. It allows for a declarative way to manage your application's desired state. That's specifying the number of replicas and containers in which to run. K8s continuously monitor the state of the microservices, ensuring the correct number of replicas are running, restarting them if they fail. By deploying microservices through K8s, you benefit from enhanced automation, fault tolerance, and high availability, making the management of complex applications significantly easier. Alright, so that was a basic overview of K8s and its role in microservices, and how they are deployed. Thank you. Welcome to this tutorial on getting started with Kubernetes and setting up environment to create a Kubernetes cluster. Now, we can use Kubernetes locally through Minikube, which we are going to be using. and this allows us to run a single node Kubernetes cluster on our local machine. Minikube basically runs a local Kubernetes cluster, and it is simple, very simple, to set up the environment for the local development. Alright, so to get started, you have to navigate yourself to the Minikube website, where you can download Minikube. The first thing we see here are the requirements. You need 2 CPU cores or more, 2 gig free memory, 20 gig free disk space, and you need an internet connection and a container or a virtual machine manager. We are going to use Docker as we have been using for our microservice. Now you select your operating system. Select your operating system. That's Windows. Then select this and then release type. There are 3 different types of installers. You can use the EXE, the package manager, or Chocolatey. We are using .exe download, so we just click here for the latest release. However, you can use PowerShell and copy the code here to download the installer. When the installer is downloaded, you start the installer. Alright, so the first option is the language you selected, and then you can click Next to continue. You agree to the terms and conditions, and then you install your Minikube. So now we have installed our Minikube. Click on Finish. The next thing is to add the minikube.exe to your path binary, to your path variables. We are going to copy this code here, and we have to use PowerShell as an administrator. You can use PowerShell as an administrator. In your PowerShell, you paste the code here, and then this has been added. Now to start a local Kubernetes cluster, we are going to use the code minikube start. Then we enter this to start a local Kubernetes cluster. Okay, so we have an error and it's telling us that it is unable to detect Docker. So we are going to have to make sure our Docker engine is running. So now you have to open your Docker desktop and make sure the engine is running. Now our Docker desktop is running. The next thing we are going to do after checking this is that we are going to run the code again. So I'm going to run minikube start, and this time it should work. But we still have an error. We now have to restart our PowerShell and do this all over again. We now see here that our Kubernetes cluster has been created. Basically, we are setting up a cluster for a Kubernetes in Docker, which will allow us to run our single node Kubernetes cluster on our local machine. We can see now that it has been downloaded, and then we see that our cluster has been successfully created. We can check this out in our Docker desktop. And we see that Minikube here has been created as a container in our Docker desktop. We can now check for the status. We will use minikube-status, and we can see the status here. Alright, so we successfully created a cluster locally, and we are ready to deploy services with our Kubernetes. Thank you. Welcome to this tutorial video on creating Kubernetes deployment and services. We've already been through an introduction on Kubernetes, and we've seen how to build Docker images and run Docker containers. So now we are going to be putting all of this together in this tutorial. So we are going to build a simple web service using FastAPI to manage a list of products, and this is our product service. This is our code for our product service, and so we're just quickly going to run through it. Alright, so the first thing we will do is import our FastAPI module, as we usually do. Then we create an instance, and then we see a pseudo dictionary here, or a database. It's like an in-memory database that defines a list of products, and each product has an ID_name and price. We will be using real-time databases in subsequent tutorials. The first endpoint is a get endpoint, created here at the /products root. Anytime someone visits this URL, the function get_products will be called, and the get_products returns the list of products in JSON format, when someone calls the endpoint. In the second get endpoint, there's a specific product that can be retrieved using its ID. So, for example, if we have product and the product underscore ID is 1, it means that it will return the product with the ID equals 1. And so line 15 tells FastAPI that the product underscore ID passed in the URL must be an integer. The next line of code searches for the product in the list by its ID. If it doesn't find one, it returns none. Alright, so the next thing is that we have to create a Docker file for this microservice. The code is already here. So we see here the base image that's Python 3.9 Slim, and we can see the working directory. So this sets the working directory inside the container app. And all future commands will be running this directory. For the copy command, this copies everything in your current directory where the FastAPI is into the app directory inside the container. And the run command installs FastAPI and Unicorn. The next thing here is that it makes port 80 available for external access. And then this is the command that Docker will use to run. It uses Unicorn to run the FastAPI app. So we are now going to build our Docker image. So this line of code here, or this command, builds a Docker image named product service from the current directory. One thing we have to do is that we have to cd into the directory where our Docker file is located. So we are going to cd into this. And now we'll run the command to build a Docker image. So we run this command, and we can see that we have successfully created a Docker image product service. Now we want to push this image into our Docker Hub. But before we do that, or before you push the image must be tagged to include the repository name. So in this case, it's going to be your Docker Hub account username. Basically, we're going to tag our product service image. We are going to give it a tag, and we are going to use a Docker Hub username. Like I said earlier, if you have your Docker desktop installed, you just log in or create an account and then you can use it. Alright, so now we've tagged it. Now I'm going to push the image into a Docker Hub. So run this code. We have successfully pushed our Docker image into Docker Hub. Now we want to look at our YAML file to build our Kubernetes deployment and service. So you open this folder for deployment.yaml files. So I'll just basically run through this. We are now going to deploy our containerized app to Kubernetes to make it scalable and highly available. So this is the code for product development.yml. The first thing here is the API version, and this tells Kubernetes what version of API to use for this resource. We can see here that this version and the kind here means that we are creating a deployment. At first, we will create a deployment, then we will create a service. Replica ensures that the right number of copies of our application are running and our metadata name is named product deployment. This is just a name for deployment. For the replica, we have specified that we want 2 instances of our product service running, so we are making it 2 instances. For the labels, this helps Kubernetes know which pods to manage as part of this deployment, in case any pods with the label product service. So any pods with product service, Kubernetes will manage it. We are essentially telling Kubernetes to manage any pods with the label product service. Then for the templates, this describes the templates for the pods in this deployment. The containers specify the containers that will run in the pod. So the name of the container is product container, and the image is the image that we have tagged and containerized and put in a pot, cut, and put in a push to our GitHub Docker Hub repository. This tells Kubernetes to use the Docker image we created earlier, and then the port tells Kubernetes that the container listing on port 80. The second part is creating the Kubernetes service. So we also see the version of the service, and this creates a service resource that exposes the deployment inside the Kubernetes cluster. The type of the cluster is cluster IP. This tells Kubernetes that the service is internal, meaning it is within. We have different types. We have the load balancer, and we have node port, which can also make it accessible externally. Then the selector links the service to ports that have the app label product service. Then the port maps port 80 of the service to port 80 of the container. So to start deployment of Kubernetes, we are going to have to first run this code. If your Minikube is not already started, you have to make sure that you have started a Kubernetes cluster using Minikube. We are now going to deploy this service. Alright, so I'm just going to clear this terminal. Now we have to first cd into our registry, where our product development.yaml is located. We cd into this directory, and now we can run or create a deployment in a service. So we create a deployment using this cut kubectl-f product-deployment.yaml, which is the name of your YAML file. So hit enter, and we should see that our deployment has been created, and our service has also been created. Now, I want to verify this, so I'm going to run kubectl get pods, and then hit enter. Alright, so we can see that our 2 pods are running, and our deployment has been created. We can also see the 2 replicas of our product deployment. We can also check kubectl get deployments. So our 2 deployments of product service are up to date and available. This brings us to the end of this tutorial on creating or deploying a FastAPI service, which is a product service on Kubernetes to make it available. In the next video, we are going to look at how to manage pods and how to scale services. Thank you and stay tuned. Welcome to this tutorial video. In this video, we are going to be looking at how to manage our pods and scale our services in Kubernetes. So the first thing, as we know, is that the pods are the smallest units or deployable units in Kubernetes, and they can run 1 or more containers, and each container runs an application such as our FastAPI product service. In the last video, we used this command, which is to get pods. And this command lists all of the pods running in our cluster. So you see the status of each pod, hit enter, and then you can see the status of each pod. It might show running, pending, or loop, back off. But here we see that our pods are running. We also have 2 pods running. Another thing we can do is describe the pod. To do this, you have to use the kubectl describe pod and then the pod name. We are using the first pod here. It's going to describe the pod. We can see that there's a description of our pod. Alright, so the next thing we want to do is use this command, which will show the logs from a specific port. This is helpful in debugging if your pod is misbehaving or crashing, because it describes what you previously did, give reasons for failure, and so on. You just hit enter here. Alright, so we see our log for that particular pod. The next thing we want to do is that sometimes you may need to remove a pod manually, for example, if it's stuck or not responding properly. To do this, you are going to use the delete command. So you can use the delete command to delete any pod here. This is the command. If you do want to delete this pod, you just hit enter here. Alright, so we made a mistake here. We were supposed to type delete pod and then the pod name. This pod has now been deleted. But don't worry. If this part is part of deployment, Kubernetes will automatically create a new one to maintain the desired number of replicas in our case. We can check this out. So we see that another pod has been created and the previous one has been deleted. Now we want to look at scaling, which is about port management. We are looking at scaling Kubernetes services. We want to scale service up, which is basically adding more pods. So let's say you have more users coming to your product service and need more instances to handle the increased traffic. You can then scale your development easily. So we are going to scale our services up to 5. This command allows you to adjust the number of replicas in your deployment. And the product deployment here is the same of your deployment. Cut. And the product deployment here has the same name as your deployment. A replica here scales the deployment up to 5 replicas, meaning that Kubernetes will create 5 pods running your product service. We hit enter and we can see that the deployment has been scaled. So we are going to check this using get pods. We can see that 3 new pods have been created. Alright, so we can also scale down our services. If traffic slows down and you want to reduce as many resources as you can scale your service back down to save your resources. This reduces the number of replicas. Once you reduce the number of replicas back to 2, meaning Kubernetes terminates the extra pods. We just use the previous code here, and then we change the value to 2 and hit enter. So our deployment has now been scaled down. We just check the pods and we can see that the extra ports have been deleted. Now we can auto scale our pods based on CPU usage. So Kubernetes can also automatically scale based on CPU usage using the horizontal pod autoscaler, which is the HPA. We are going to use this code. You are essentially telling Kubernetes to autoscale deployments, then the name of your deployment service. This means that if the CPU goes over 50%, Kubernetes will create more ports to handle the load. Then this sets a minimum of 2 pods and a maximum of 10 pods. So if the percentage goes over 50, more pods are created and the maximum pods that can be created is 10, with the minimum being 2. So go ahead and hit enter. Our deployment, or our service, has now been auto-scaled. You can check the status using kubectl get HPA. Remember, HPA is your horizontal pod autoscaler. Alright, and we can see this here. In Kubernetes, we can also do rolling updates and rollbacks. Kubernetes makes it easy to update your application and ensure the update happens without downtime. So if something goes wrong, you can go back to the previous version. So let's say I've made some updates to your product service Docker image, and we still want to deploy it. If you want to change this image and you don't want your service to experience downtime, you can just update your deployment using this particular code. So the set image updates the image used by the deployment, and then the deployment /product-development specifies the deployment being updated, which is our product development, which is our product deployment and product container, which is our product-deployment and product-container equals product service v2, updates the product container to use the new version of the image. So if your image has been changed, you can update it using this code, and you can also roll back to a previous version. So if this new version has a problem, you can roll back. So now let's use our get pods, and we can immediately see that there is an error. So we are going to roll back to our previous version. This code basically rolls back to our previous version. Alright, so we can check out our pods using get pods, and we are back to our previous version. This brings us to the end of managing pods and scaling services in Kubernetes. You can ensure that your application is always available regardless of the traffic. And you can add more resources when needed and reduce them when traffic slows down. And you can also do rolling updates and rollbacks, which give you the flexibility to manage new versions without risking downtime. Thank you very much. Welcome to this tutorial video. In this tutorial, we will create a simple FastAPI microservice that logs messages using Logstash, and that will configure to send log entries in JSON format over UDP, which is User Datagram Protocol. This is a communication protocol used across the internet, just like TCP, which is Transmission Control Protocol. UDP is a connectionless protocol, unlike TCP, which is connection-oriented. So this setup will allow us to capture and manage logs effectively using Logstash. Logging, as you may know, is the process of recording information about an application's execution. So log captures details about events or actions within a system, such as errors, status updates, and user interactions. In Python, logging is typically implemented using a logging library, which allows developers to specify log levels. Now, Logstash is an open source tool, part of the Elastic Stack, or ELK stack, along with Elasticsearch and Kibana, which is used to collect, process, and forward logs and events from various sources. So Logstash can gather logs from application servers and database and other sources, filter or format them as needed, and then forward them to storage solutions, like Elasticsearch or other outputs. So the setup in this tutorial is going to help us be able to record our logs using Logstash. In this, the project structure, we have our application code. We have our docker-compose.yaml for our two services, which is a FastAPI service and Logstash. We also have a Docker file from which we are going to build our Docker image for our FastAPI service. And then we have our Logstash configuration file, in which we are going to use to configure our Logstash. The first thing we will do is look at the application code. We need to import the necessary modules, and then we can configure our logging. So, for our logger configuration, we need to configure logging, not login. So now for our logger configuration, a logger is configured to log messages. We set its level to info, which means it captures all the messages at this level and above. We also have a custom Logstash handler. This creates a custom logging handler that sends log messages to Logstash via UDP. And the emit function formats the log messages and sends it to Logstash. That's the emit function. The Logstash handler is set to be exposed on this particular port, which is port 5000. This is all part of the custom Logstash handler. This is how we set up our Logstash handler. Then we have our endpoint, our two endpoints, which is our root endpoint /, and the dynamic endpoint, which is items /item ID. We are saying that whenever this endpoint is accessed, or whenever GET requests are made to the root endpoint, the read_root function is called, and your logger info is root endpoint access. This is the message sent to Logstash. We can see this on our browser. Hello, FastAPI with Logstash, as the message sent is root endpoint accessed. For the second endpoint, The message to Logstash is item input access with item underscore ID. And this is the particular item underscore ID entered in the URL. Then we see in our browser item underscore ID and a particular item underscore ID inputted in the URL. So we have a Docker file. With our Docker file, the base image is Python. Our working directory is /app. We are going to copy this into the container from our project folder. We are going to install dependencies, FastAPI and Unicorn, and the command for executing the application is Unicorn. Now we can move to our docker-compose.yml, and we can see the image here is Docker Elastic Logstash 8.10, which is the Logstash image. The container name is Logstash, which is exposed on 5000 port 5000 UDP, and this is the volume for Logstash. And we see our FastAPI service. This is built from a Docker file and it depends on Logstash. So our port will be exposed on port 8000. Now we move into our Logstash configuration. So the first thing is that we need to input configuration. This section configures Logstash to listen to UDP input on port 5000 and expect incoming log entries in JSON format and the output configuration for that. The logs received will be printed to the console in a readable format using Ruby debug codec. Alright, so now we have explained all of this, I'm now going to run docker-compose up to build and run our containers. Our containers are already created, so the code just runs them. Alright, so we can see that our 2 servers are up and running. We'll now go to our browser to check or access the endpoints, and then we can check our Logstash to see the logs for our application. So you can proceed to localhost 8000. And we now have this message. We also want to proceed to items/1. Alright, so we are going to check this in our logs for Logstash. So we see for our first one that the root point was accessed. It gives you the date and time and the version. And you can see for our second endpoint that the item endpoint access with item underscore ID equals 1. So in this tutorial, we have successfully set a simple FastAPI microservice that logs messages to Logstash. And we use Docker to containerize both services, ensuring that they can communicate with each other. This allows for centralized login and makes it easier to monitor and manage applications. All of this setup can be enhanced by integrating more features, such as logs to Elasticsearch or analyzing them with Kibana. Thank you very much and stay tuned. Welcome to this tutorial on monitoring MicroPython microservices. In this tutorial, I'm going to look at how to monitor our microservice using Grafana and Prometheus. So, what is monitoring? Well, monitoring refers to continuous observation and assessment of a service or system, performance, health, and behavior. It involves collecting matrices, logs, to ensure the application and services are operating correctly and efficiently. We are going to be using Prometheus and Grafana. Prometheus is an open source system monitoring and altering toolkit designed for reliability and scalability. It collects matrices for configured targets at specific intervals, and it evaluates rule expressions and can trigger alerts if certain conditions are met. Prometheus uses a powerful query language called PromQL for querying time series data and Grafana. Grafana is also an open source data visualization, a monitoring tool that integrates various data sources, including Prometheus. It allows users to create interactive and customizable dashboards to visualize metrics. Grafana Grafana provides a user-friendly interface for analyzing and interpreting data through graphs and charts. We're going to zoom into our code to set up monitoring using Prometheus and Grafana. The first thing that we do is to set up our FastAPI microservice, which is a simple one. So we are going to create a new directory. You can name it FastAPI_Prometheus. Then you can create your virtual environment and activate it, and then you install. So we are going to install our dependencies. We're going to install FastAPI, Unicorn, Prometheus-FastAPI-Instrumenter. And this is what you will be needing to set up Prometheus and Grafana for our FastAPI service. Alright, so our dependencies are already installed. The next thing to do is to create our main.py. Our main.py is where we are going to have our FastAPI microservice. So first, we import libraries and modules. FastAPI is a framework for building the microservice, and the instrumentator is basically a utility from Prometheus-FastAPI-Instrumentator that helps expose Prometheus metrics for FastAPI applications. So we do the initialization of the app, and then we create an instance of instrument data to collect metrics. We are saying that this line registers the FastAPI app for metrics collection and exposes the metrics endpoint for Prometheus to scrape. Scraping just refers to the process by which Prometheus collects metrics from monitored targets, such as the applications or services like we have, or even databases. So we have two endpoints. Here we have a get endpoint, which is a root / endpoint that returns a JSON response. Then we have an endpoint that takes an item_ID and returns it in the JSON response. The next step is to containerize our FastAPI using Docker. So we just create a Docker file in the same directory, and then we specify the base image to use, the working directory. We copy our requirements.txt from our current folder. Then we install the required Python packages in our requirements.txt without caching. So these are requirements, FastAPI, Prometheus-FastAPI-Instrumentator. And then we copy the rest of the application code into the container. Then we can specify the command to run the FastAPI using Unicorn. Now we need to set up Prometheus. And to do so, we are going to use a YAML file. So we create a file called prometheus.yaml. The global sets up the global configurations for Prometheus. The scrape interval, we've explained what scrape is previously, but the scrape interval is the interval at which Prometheus scripts metrics from target. The script configuration configures which endpoint Prometheus should scrape. And the job name equals FastAPI means that the name of the job identifying this particular scrape configuration is FastAPI. The specific target for scraping is an array of targets where FastAPI:8000 refers to the FastAPI service running on port 8000. We now set up our Grafana on our Docker Compose. Basically, we are going to build from our Docker file for our FastAPI service here. That's the name. That's the job you see here. For Prometheus, we build from an image prom/Prometheus. And for Grafana, you also build from an image Grafana/Grafana. Then we see the port on which they are exposed. The next thing to do is to run the application. We are just going to use docker-compose app and build. Then we enter. So our services will now begin to run. Grafana and then Prometheus, as well as our FastAPI-service here. The next thing we are going to do is that we are going to access the applications. So we need to open our browser. When you open your browser, go to the URL localhost:8000. Then, when in another tab, navigate to localhost:1990. You should see Prometheus dashboard and can use it to explore the available metrics. Alright, so you can check the status of our target, which is a FastAPI. We can also go ahead to Grafana. When you go to Grafana, it's going to take you to a login page. Admin is the default username, and admin is the default password. It's going to ask for you to set up a new password, so you can do this and confirm it. You can also decide to skip that if you want. We are now going to add Prometheus as a data source. In Grafana, we're going to click on the G icon at the top left for configuration. So look for the G icon and then click Go to Data Sources. Then you add a data source, select Prometheus, and then a URL, which is 1990. So http:/localhost:1990, and then click Save and Test. We have an error here. I think it's because we are using the local host, because we have our Prometheus running in a Docker container. So we can just change this. We are going to use this URL for Prometheus because we are running it in our local Docker container. And we try it again. Alright, so the next thing I will do is that we build a dashboard. We are going to go to Add Panel, then Add Visualization. We select the metrics, which is HTTP request total. We can see the HTTP request total here, and then we can click on Apply to add it to our dashboard. So HTTP requests total gives the number of requests that has been made to a particular service endpoint. So you see it here on our dashboard. Okay, so in this tutorial, we have been through creating a simple microservice containerizing Docker, setting up Prometheus and Grafana, and to visualize FastAPI metrics and monitor health of microservices. Welcome to this tutorial video on distributed tracing for debugging FastAPI microservices with Jaeger. In this tutorial, we'll walk through setting up a distributed tracing system for FastAPI-based Python microservices using Jaeger. Essentially, distributed tracing helps you to debug issues across microservices by showing how requests travel through different services in your system. Distributed tracing provides developers and operation teams with the insight needed to monitor application processes' performance, troubleshoot issues, and ensure a smoother or a smooth user experience across different services. So now you understand what I mean by distributed tracing. It is essentially maintaining and optimizing microservice architecture. Alright, so we are going to go straight into this tutorial. The first thing we need to do is set up our project. First, you need to set up a directory. You can name it FastAPI_tracing or Jaeger tracing. Then we are going to install our dependencies. However, before this, we need to create our virtual environment. So we create our virtual environment and activate it. The next thing we do is install our dependencies. So we want to install FastAPI, Jaeger-client, and Open Tracing. Jaeger client is the Python client for Jaeger, which allows us to send tracing data. Open Tracing is a standard library for distributed tracing, which Jaeger client implements. The next step is to create our FastAPI application in app.py or in main.py. First, we import our libraries and modules. So now we import FastAPI to build our microservice framework. Open Tracing is a library that provides a standard interface for distributed tracing, and we'll use this to integrate tracing into our app. Jaeger client is Jaeger's Python client for handling configuration and sending tracing data to Jaeger backend. The next thing we do is initialize our application, which will define our routes and handle our request. Then we go to Jaeger tracer Jaeger tracing initialization. We are going to initialize Jaeger tracer. The service name specifies the name of the microservice in Jaeger UI, which is FastAPI-Jaeger. And then the sampler controls the requests. At least in this case, we are using a constant sampler, which is type::const. That means it samples every request. Logging is also enabled for debugging processes for debugging purposes. Finally, we call config.initialize_tracer closed brackets to get the tracer object. We create the tracer object using tracer equals init_tracer closed brackets. This creates a global tracer that will be used throughout the app to trace requests. And then we define our FastAPI endpoint. We define a root endpoint that retains a basic hello world message. And then start _active_span, which is a function that creates a new trace span called root endpoint that captures the request processing time and metadata for this specific route. Then we see another example where we use tracing for dynamic routes, items/item_ID. So each time a request hits this endpoint, the trace captures how long it will take to process the request and which parameters were used. Now we are going to run our application. We will use Unicorn as the name of our file, the name of the app, and then reload. So we have made a mistake with the spelling of Unicorn, so we will just correct that. Now our first API is running locally at the URL specified there. The next thing we need is to set up Jaeger. Jaeger can be easily run using Docker, and we are now going to run a certain command. To start Jaeger, we are going to run this code. We are basically running Docker in all-in-one mode, and 18686 is what we are going to use to access the Jaeger UI. And all other ports are for internal services that Jaeger used to collect trace from your data app. We are just going to hit enter, and we can see that right now our Jaeger image, or the images, have been pulled, and the container is running. The next thing that we are going to do is navigate to our browser. So we go to our browser and navigate to a URL on which our app is exposed. Our FastAPI app is exposed, right? So we just head to our localhost :8000/docs to get the documentation. We can just execute this. When I execute this, you get a response message, hello world, and that's for the root /endpoint. For the get items endpoint, you can just try it out and execute. You can execute twice. Then you open your Jaeger UI using this localhost :16686. So what you are going to do is select your FastAPI. For the name of your application or your service from the the name of your application or your service from the drop-down, and then click on Find Traces. When you click on Find Traces, you should see something like this. So if you do this, you should see the traces. This is for the item endpoint. If I click endpoints, you can also see that when you click Find Traces, you find out that you see the traces. So using Jaeger is simple. Now just go to the search and look for your name of your service. You click it and then find traces. It essentially monitors, and you see the time here, 0 microseconds, the time it took to execute, and you can also see the duration. That is essentially everything about using Jaeger. Overall, Jaeger is a powerful tool for understanding performance and diagnosing issues and complex microscopic service architectures. So when you have complex service architectures, you can use Jaeger to monitor. This is the end of the tutorial. Thank you. Welcome to this tutorial video on writing unit tests and integration tests for microservices. Unit testing and Unit testing and integration testing are both essential components of software testing, but they focus on different aspects of the software development process. For unit testing, The testing of individual components or functions of a software application in isolation. The goal is to verify that each unit of the software behaves as intended. As for integration testing, it focuses on testing the interactions between components or modules of an application. The goal is to ensure that these components work together as expected. So, in this tutorial, we will build and test a simple FastAPI microservice that handles retrieving items from an in-memory dictionary. And we will write a unit test to ensure that the endpoints work as expected. Okay, so we have our file service.py, and for service.py, we first import the FastAPI library, and then we create a new FastAPI application instance. Then, this is our in-memory dictionary. And then we have endpoint. We have an endpoint /item/item_id, and this read_item function is triggered when a request is made to items/item_id. It looks for the item_id in the dictionary and returns the corresponding data or error message if the item doesn't exist. Alright, so to test this simple microservice, I'm going to use test_service.py. This test is to verify that the endpoint works correctly. As we can see here, most of the comments explains the code. So, the test client app creates the test client for our FastAPI application. It allows us to simulate requests to the API without actually starting a web server. And then, this function, test_read_item closed brackets, sends a GET request to items/1 and verifies that the response status code is 200. And for the text_read_non-existent_item, this function sends a GET request to /items/999, which doesn't exist, and verifies that the status code is still 200. This is because FastAPI always returns 200 unless there's some internal error, and it asserts that the response contains the error message, error item not found. So we are going to run the test. But before, you have to install our dependencies and also our virtual environment. Alright, so I've now created our virtual environment. I have also activated it. Now we are going to install FastAPI and pytest. So FastAPI is the framework for the FastAPI application, or the microservice application. Pytest is for testing microservices. So now that we've installed this, we can simply test our service. So we type pytest test-service.py, and we have an error. So we have to install httpx because it's needed by the test client. So we are going to install this and then run the code again. Let's clear this and run our code again. Wonderful. So our test passed with 2 items in 1.73 seconds. Now we're going to go to our integration testing. So we've created 2 microservices, microservice A and microservice B. Then we'll write an integration test to ensure that service A can successfully communicate with service B. So let's look at service A. For this, we import the libraries and import requests to send HTTP requests to other services. We create an instance of our app. We then define an endpoint that is /call-microservice-b. So this endpoint makes an HTTP request to microservice B at this particular localhost :8001 anytime a GET request is made to this endpoint. So, anytime a GET request is made to this endpoint, the /call-service-b gets the response from this particular URL or this particular link. Then, a JSON response is received, and it prints the response gotten from this particular URL. Now we can look at microservice B, which is service_b.py. This is a simple service. We import FastAPI, create an instance with the application, and define an endpoint, which is named /endpoint, which returns a message, hello from service B. This message is what is received by service _A and printed out to show effective communication. Alright, so we want to look at our test _integration.py to test our two microservices. First, we import process from multiprocessing. This allows the script to create and manage separate processes. This is for running each service in its own process, enabling them to operate concurrently. Then we import FastAPI.testClient. TestClient is used to create a test client for making requests to applications without... So it's like assimilating requests to your app as if they're coming from a real client. And the time library is used to include delays in execution of the script. This is like when you are waiting for a microservice to start before the testing. And then the requests is for making HTTP requests. Then we are importing the FastAPI application instance from service _A, and we are giving it an alias of app _A, which is the same as giving it a nickname. And then for service _B, we import our application as app _B. This line imports the FastAPI application instance from service B, nicknaming it as app _B. Now, run _service _B closed brackets is a function defined to start service _B. So, you import Uvicorn, which is the ASGI server, and then you run it. So this line starts the FastAPI application defined in service _B on the local host at port 8001, and the Uvicorn will serve the application, allowing it to respond to incoming requests. And then the tests _call _service _B closed brackets function is defined to test the interaction between service _A and service _A, and process _B equals process. Bracket target equals run _service _B close bracket. This means that a process is created to run service _B, and the target function is run _service _B, which will start the service. So process _B starts the newly created process, which will run service _B in parallel. And then we go to test client for microservice A. Client _A equals test client bracket app _A close bracket creates a client for service A, allowing it to make requests as if it were a real client. Try begins a block to ensure that the following code is executed while also allowing for cleanup in case of an error. So, response equals client _A.get /call -service -B simulates a GET request to the endpoint /get -service -B, which is an endpoint of service _A, which is also an expected call from service _B. So the assertion response.status.code equals 200 checks that the response status code is 200, indicating a successful request. And the next one, that is the next assertion here, checks the JSON response, whether the JSON body matches the expected output, verifying that service A successfully received its message from service B. And finally, the process is terminated. Then the new block of code is to run the test directly if the script is executed. So we are going to run pytest _integration.py, and you can see that it is successful. This has been a tutorial on creating unit test or a creating test and integration test for microservices. We have talked about integrated unit tests being tests of particular parts of the application in isolation, and integration test is interaction between different parts of the application. Thank you and stay tuned. Welcome to this tutorial video. In this tutorial, we're going to be setting up a cluster, a Kubernetes cluster on GKE. That's using our Google Kubernetes engine on our Google Cloud Platform. In our next video, we will be looking at creating a CI/CD pipeline for GitHub Actions. Now, CI/CD is continuous integration. Continuous deployments, meaning that for the integration, it means integrating code changes from multiple developers in a shared repository, and it can also include automated testing to ensure that real reliability of the merged code. And then we have continuous deployment, which automatically deploys the integrated code to production. So, we are looking at deploying microservices to production, setting up a CI/CD pipeline with GitHub Actions, and we will also be using Google Artifacts Registry. We are now going to build our images, our Docker images, and this time we are not going to push Docker Hub, but we will go to our Google Artifacts Registry. From there, we are going to deploy a cluster in our GKE, which is our Google Kubernetes engine. All right, so the first thing that we want to do is create an account on our Google Cloud. Now, you can create a free account, which gives you $300 credit for the first 90 days, and then you can create a paid account. The first thing, though, is to go to cloud.console.google.com after creating, and then you sign in. Then you go to this drop down and go to create new project. Now you can create a new project and name it FastAPI-project, as we can see here, and then click create to create a project, but you can name it anything you want to. Our project is now created. The next thing that we are going to do is click the project and open it. Then we are going to go to IAM and admin and select service accounts. We're going to look for service accounts and then select service accounts. After this, we are going to create a service account. So we are now creating a service account for our cluster. We will be naming our service account here, and you can choose a name. We are going to name our service account, and then we create and continue. The next step is the access. I'm going to select a few roles. The first role is Kubernetes Engine Admin, which enables us to create clusters and manage them. In the next role, we are going to create Artifact Registry Administrator to be able to push images into our Artifact Registry. So we select this. We select another role, which is Service Accounts User, and then select Continue. The next thing we do is grant access to the service account. So we're just going to click Done here. We now see that our service account has been created. The next thing for us to do is go to Keys, then Action, then Manage Keys. We are now going to create a new key, which we are going to use in our CI/CD actions. We select JSON to create the key. This key is very important to be able to access your GKE cloud or GCP cloud. When writing the workflow.vaml file for our CI/CD, we'll get into this in the next tutorial so you can get a hang of it. Now we are going to create a cluster. So go to Google Kubernetes engine and select clusters. So we are first supposed to enable this API to be able to generate clusters on our GCP cloud. So we go to create here, we click it, and then we can just leave the name as Autopilot Cluster 1. We choose the region. These are all important things that we are going to be using in our workflow file. Then we go to fleet registration. As we can see on the screen here, we make all the necessary selections and deselections as we see on our screen. Ensure that you have selected the right things and deselected some as well. Because of our advanced settings, we will not be making any corrections or selections. So we will just go to Create Cluster to create our cluster. Then we see right here, our cluster has been created. So go to connect to the cluster. So we click Connect, and then you should see a code popping up here. A line of code, and you copy the code to the clipboard. We are going to run this. You can run this locally, or you can run this in your Google Cloud Console terminal. So we are going to open our terminal and input the code to connect to our cluster using our command line. If you want to do it locally, you must have installed gcloud. So we authorize this, and now we are connected to our project. And also our cluster. Now we go to Artifact Registry to create a repository to which our Docker images will be pushed to. So we click Create Repository. We will just name it Microservices or Project. The format is Docker standard. Then you choose a region. Make sure your region is the same of your service account, and then so all the other options should be left as it is. Make sure to select all these and then create. So we are creating a repository to which our Docker images are going to be pushed to. We can also add permissions, but naturally this folder is going to inherit permissions from our service account. This brings us to the end of this tutorial. Next video, we are going to be creating our CI/CD pipeline for GitHub Actions. We are going to use all the credentials that we have used here in settings. We are going to use all the credentials that we have used in setting up our cluster for Google Kubernetes Engine. So stay tuned. I'll see you shortly. Welcome to this tutorial video on CI/CD pipeline for a FastAPI microservice deployment to GKE using GitHub Actions. In this tutorial, I'm going to give a step-by-step guide for deploying a FastAPI microservice to production on Google Kubernetes Engine using GitHub Actions. Now, in this setup, we're going to have 4 files, and we're going to have a Docker file for building a Docker image, which is our deployment.yaml for specifying our deployment and service, and main.py, which is our microservice, and then our requirement text, which is used for building from the Docker file. We also have our ci_cd.yaml. In this tutorial, we're going to be deploying our service. In our previous tutorial, we set up our cluster on Google Kubernetes. In that setup, we created a project_ID. So you can see your project_ID from this window. We then created our FastAPI project. So this is a project_ID which we used. Then click this. We call that our region, which is US Central. We also created a repository named Project in the Artifact repository. Artifact repository was named Project, and that location was also US Central for our repository and then also for our cluster. So if you go here to Kubernetes Engine, you can see the clusters we have. Our clusters are autopilot-cluster1. All these variables are part of our environment variables. For our ci_cd.yaml pipeline, this defines the process for our ci/cd for GitHub Actions. We are saying that on any push to the branch master initiates this pipeline. These are the environment variables, and the job is called deploy dev, and it runs on ubuntu, and then the environment is dev, and these are the various steps. So first, you have the checkout code, which checks out the repository, which we are using for our GitHub Actions. It checks out the repository for the GitHub Actions runner. The next step is essentially for building Docker images, and the next step is for caching layers. So we are saying that to speed up the Docker build, we are going to cache the layers of the Docker image and commit hash. Cut and use the commit hash. Anytime there is a change, there's a new commit hash per build. The next step is authenticating to GCP. We are authenticating to Google Cloud using a service account key as a secret. So this is a service account key as a secret. Then we have the environment variable project ID. Then we set up Google Cloud Software Development Kit, which also uses the project ID and also the service account key. Remember how we got our service account key from the previous tutorial. The next thing here is that we are going to see a configure Docker. This allows Docker to use gcloud for authentication when pushing to Google Artifact Repository. We are going to be using Google Artifact Repository and authenticate it first. We are allowing Docker or configuring Docker to use gcloud for authentication. And then this is to build tag and push image to Google Artifact Repository. So this builds a token image, used cached layers, and pushes it to Google Artifact Repository. The --cache- form uses cache layers for faster build times, and the --cache-2 saves the new cache after building. Okay, so we are essentially using the tag, the region, the project ID, the name of the repository, and the image name, and then the image tag. So the image name and the image tag are not of the environment variables, which you can decide to choose. You can choose anything. Then we are going to set up GKE credentials, Google Kubernetes credentials. This configures KUBECTL to authenticate with the GKE cluster. So we are going to authenticate to set up KUBECTL. And then we finally deploy the FastAPI Microservices to GKE using the Kubernetes file k8-deployment.yaml. What do we use? Then we see our k8-deployment.yaml, which specifies the deployment and the service, so we can see the image name here. If you look at your ci_cd.yaml, if you look at this part, you see your region, your project ID, your repository name, and image name, and image that in that manner. You also see it here. So region project ID, the name of the repository, the name of the service, and the tag. These are the resources allocated for the application. We have a microservice using cluster IP. Using the service type cluster IP, and this you can exchange cut. Using the service type cluster IP, and this you can change to load balancer or import when you want to expose. So we have our main.py, which is a simple microservice with one endpoint, and we are going to print the message hello ci/cd with Kubernetes. I know deploying the service will not be as simple as this. An application will probably have different parts, and a lot of them, but just to simplify this explanation, this is why I've chosen this code. So we have a Docker file from which we will build our Docker images, a base image, a working directory, and a copy of our requirement that texts it to our container. Then we run it, we install it, and copy contents to our container. Then we use unicorn as a command to run the app, and we expose it on port 80. Our requirement.text is basically FastAPI cut. Our requirement.text is basically FastAPI and unicorn. Alright, so now we are going to go to our GitHub repository to create a new repository, and then name the repository FastAPI-project. So FastAPI-project, and then we leave all other options and we just click Create Repository. Essentially, I'm going to copy this URL, which will be used to connect with our local repository. The first thing we are going to do is initialize the repository, and then we are going to add. So we're going to use git add, then the current repository, and then the next thing we're going to do is commit. So anytime you make a change, we're going to name the comment. So rename new commit. The next thing that we will do is connect using our URL that we copied. So we type git remote add origin, and then we add our URL here. So we paste our URL right here and hit enter. The next thing to do is push into our GitHub actions, our GitHub repository. So we have successfully pushed our code. Now let's go to GitHub. When we go to actions, you can see that the job has started because you are starting on push to branch master. And we see that there's an error here because we did not our secret keys. So we now go to the settings, secret and variables and actions. In our actions, we are going to add a service amount key. So our Google Cloud Service account key. We click on new repository secrets. We type GCP_SA key, and our secret is our JSON file. which we generated while setting up our cluster on Google Cloud. Now we are just going to open Notepad and then copy the contents of this here. We are going to paste it in our GitHub repository as a secret. We click Add Secret, and now our secret is added. And we are going to return our jobs in our Actions GitHub Actions. So to do this, click on Actions and we rerun the job. Click on the name of the comments, New Comments. Click on it. And then we select Rerun Jobs. We rerun all of the jobs. Return the jobs. And you should see that after some few minutes, your deploy dev, which is the name of your pipeline, will be completed. The job will be completed. You can select this to see the details and the processes, and we see that every step has been ticked. This means that we have deployed our service to GKE, and when we go to our Cloud Console, we see that our FastAPI-deployment is running. FastAPI-microservice with one pod. Now we can see the content of this service. We can see our pods and service by just clicking on the name of our deployment, and it's going to open a page for us, which will show us logs of our services and our pods, and a lot of more information about pods. So you can go to Actions, then Expose to see this, and we just click on Expose, which means our service has been exposed. So we want to visualize our logs for our service, which was created, and we see the logs here. And so we go to Workloads, click on the deployment again, and we are going to scroll down. Now we are going to see the ports on which our service is exposed. So we see our pods here, and you see the ports on which they're exposed via Load Balancer. So we just select this link and click it. We should see our service here with message hello CI/CD Kubernetes. And this brings us to the end of our tutorial on deploying microservices to production on GKE. Welcome to this tutorial video. So we've gone through the course syllabus for Python Microservices, and this is just a brief summary. We started with the microservice architecture, and then we explained how microservices can be reduced to applications, small applications, for independence and scaling and development. We also talked about why Python is suitable for microservices, which is for simplicity. Its rich libraries and compatibility with frameworks like Flask and FastAPI. The next thing we did is set up our development environment. We installed Python and Python's package manager, which is pip. Then we set up our virtual environments using Studio Code. I did, however, say that you can use any other IDEs like PyCharm, etc. The next thing we did is look at the framework of microservices. We also compared FastAPI with Flask microservice, and then we created our first microservice. We went through a step-by-step guide on how to do so. We were using FastAPI, but we also used Flask. And then we looked at endpoints and routes, how to define them, and how to handle the HTTP method for CRUD operations. So with the get, post, put, and delete method, and we looked at guidelines for returning JSON responses formatted for readability and compatibility with other services. The next thing we did was Docker. We explained what Docker was. We created a Docker file for a simple microservice. Using FastAPI, we built and run our Docker image, and we configured, or went through how to configure, environment variables. The next thing we did was inter-service communication. We covered how do microservices communicate with each other. So we covered RESTful APIs for synchronous communication. Synchronous means that you need a response immediately. We also looked at asynchronous communication. We also looked at asynchronous communication using message queues. And in this part, we did asynchronous communication using RabbitMQ. Then we also looked at data transfer using gRPC. The next thing we did was set up a local PostgreSQL. The next thing we did was managing state and data persistence. So we set up a local PostgreSQL database, and then we connected it to our microservice. We then established database service patterns, and we used Redis for caching to improve performance of our microservice. The next thing we looked at was implementing security for microservices. We used JWT to verify user identity and control access. We used JWT to verify user identity and control access. They also used our API gateway. We also did a tutorial on API gateway for managing incoming requests through a single entry point for 2 microservices. Then we looked at secure communication with SSL and TLS to ensure confidentiality and integrity. Then we moved on to Kubernetes. We explained what Kubernetes were, automated deployment, scaling, and the managing of containerized applications. We also looked at Kubernetes deployment and services. We defined the desired state of application, which service enables stable network access with Kubernetes. And we looked at scaling services and managing pods with your microservice application on Kubernetes. Then we looked at monitoring and logging. So we used Logstash for logging and Prometheus and Grafana for monitoring. Prometheus collects metrics, while Grafana helped us to visualize performance and provide real-time monitoring capabilities. We showed you how to integrate all of this with a database with your microservice. Then we looked at distributed tracing with Jaeger. Jaeger traces requests across services, aiding identifying bottlenecks and debugging issues. So we basically looked at setting up all of this with your microservices. Then we went to writing unit test and integration test. We set up our Google Kubernetes engine and then our CI/CD pipeline with GitHub Actions. We automated a deployment on the GCP cloud on Google Kubernetes engine, and we pushed the image to the artifact registry, and from there, we deployed it on GKE. So now we go to our next steps and advanced topics. This essentially provides an overview of how to go about each step of the process. But you can work on a project which combines a whole lot of things, which will of course take time and a lot of coding. But this is basically a template for you to create any microservice project. Then there are some advanced topics you can look at, such as resilience and fault tolerance, and data management patterns, security and best practices, service mesh, advanced configuration, multi-cloud and hybrid cloud development, serverless microservices, and function as a service. After this, you can then look at GraphQL for microservices, compliance, and auditing in microservice. These are some of the advanced topics that can be looked at after you have grasped all of the concepts of microservices. Thank you so much for going through this tutorial with me, and we'll see you next time.